What is up, everyone? Welcome to the final ever exam review video. Before we begin, I have a couple quick announcements I want to make. Number one, this is called a final exam review video, but it's not cumulative. Like, it has all the new stuff. Maybe a couple small things from the past, but 98% of it is the new stuff. So if you need assistance with all the previous content like IR, mass spec, Diels-Alder, or aromatic reactions, I have 10 plus hours worth of videos on that already posted. So you're more than welcome to access those. And I also would highly recommend brushing up on your old content, because although the final is majority going to be new stuff, according to one of my sources, it's like 60 to 65%. So that leaves a good 35 to 40% of old content. So definitely make sure you know those, especially like benzene reactions, because I can definitely picture them combining benzene reactions with some of your new things like amine reactions. As far as like, the first exam stuff like IR, NMR, I understand for most of y'all it's a pain. Still, like, make sure you know what you're doing, but it's not going to be as on steroids as it was in the first exam, because it's not a priority here, but still be able to interpret your graphs and all that. Okay, the second announcement I have is, there's a common trend I've noticed, common complaint or just thing that I've heard from people is that, they'll say your review videos are so long that I just completely avoided it. I didn't even watch a single second of it. And I'm like, okay, how did your exam go? And they're like, yeah, I knew everything except one topic, like Diels-Alder, for example. And that ended up being half of the exam, and so I didn't do good. And I'm like, there was only one single topic you didn't know, and you didn't even approach the video. And they're like, yeah, it was too long. I'm like, bro, I have an agenda on the side for a reason. Nobody is forcing you to watch the videos or, video in its entirety. You can simply just scroll to that one topic you don't know, those one or two topics. You don't have to watch things if you already know how to do them. Now, like, I'm probably going to include timestamps this time in the description so it's easier to locate whatever topic you want to go over, but it's also not that hard to just scroll through the video. So I better not be hearing this complaint, because I don't know when this video will be posted. I don't know when you're going to be watching it, and I don't know how long it's going to be. But if you're in the situation where you just don't have time to watch the entire video, just scroll to the part that you need extra help on. Okay, this applies to all the previous videos as well. I'm not going to go ahead and tell you to watch all 10 hours of my old videos. Just watch like an hour, 2 hours max, depending on what fits your needs, okay? Yeah. Okay, I have a third announcement, but it's just actually like related to this stuff now. So I always tell people in the past, bare minimum is to just memorize your reactions, because I understand, like, when I was a student, I didn't care about mechanisms. I just thought they were like difficult to learn. And so I would tell people to memorize, because that's what I did. But this is the one exam where I think like memorizing might not be the best, because as far as I remember, like, the questions are a little bit harder. Like, it's not, okay, in the past, it's like you memorize a reaction and you recognize it on the exam and it's good. This time they can throw the reaction at you in like a different variation, and like, if you don't know what you're looking at, you might not be able to connect the dots, if that makes sense. So I would try to know what's going on. The good thing is that a lot of these reactions have a very similar concept, which I'll mention right now, okay? When it comes to carbonyls, like ketones and aldehydes, anytime you have a nucleophile, like a nucleophilic attack, it will participate in what's called addition chemistry. So addition chemistry means you're just adding things, you're not replacing anything. So if you were to attack this ketone or aldehyde with the nucleophile, all that's going to happen is you keep everything the exact same, but you add on something, which is the nucleophile. And of course, this can become protonated. You're just adding. There's nothing being replaced here, right? This applies to ketones or aldehydes. But if you have a carboxylic acid derivative, or in other words, something with a leaving group, it's going to participate in substitution chemistry. So substitution chemistry, as you can probably infer, means you're going to substitute something. So if you have a nucleophile and you attack the carbonyl, sure, at first you're going to have everything together, right? Nothing got replaced yet. But ultimately, as a lot of you are aware, you kick off the leaving group. And what happened here the chlorine is gone and you replaced it with the nucleophile. So this concept of attacking a carbonyl and staying open if you're a ketone aldehyde, or kicking off a leaving group if you have one, that's a very common theme amongst all of these, or not all, but like a lot of these reactions. So if you can understand this, it will help you a lot. All right. So yeah. Let's go ahead and begin though. Organometallic reagents. Don't be scared. This is just referring to your Grignards, organolithiums, and your Gilman reagents. So there's not much I want to say because we should be pretty proficient at these. But if you're not, it's okay. We're going to go over it real quick. By the way, in case you don't remember, the CULI, it's just written like this. There's going to be two of the thing that you're trying to attach. But don't worry, it's just one that you're attaching. It's just like there's two of them on the actual molecule, but you only end up adding one of them. This is just how we write it because that's how it actually looks, but don't be scared, okay? So Grignards, we should be especially proficient at because we've seen this a billion times since OChem 1. What do Grignards do? When it comes to ketones in aldehydes, the Grignards will attack one time. When it comes to all the derivatives of carboxylic acids like acid chlorides, esters, thioesters, etc., you attack twice. Now, how does this work? I'm going to try to zoom through it just because, once again, I've went over this like a billion times in the past. But you have your ketone here, and you're going to have your, let's do a 2-carbon Grignard reagent. The carbon that's attacking, you can think of it as a nucleophile. It's going to attack the electrophilic carbon and kick the pi bond up. When you do this, you're going to get an O negative and the Grignard that you just attached. Now, anytime an O is negative like this, it always attempts to reform the pi bond. But it only does that if there is a group to kick off. And since we're dealing with all carbons, or even if we had a hydrogen present, those do not count as leaving groups. Okay? Carbon can only be a leaving group in one specific instance, which you'll find out later on. But since this is stuck like this, you eventually get protonated. This is just a workup step, and you get an alcohol. But as you can see, the blue thing is the Grignard. We only attached it once. That's why I said 1x, one addition. Now, what if we had a carboxylic acid derivative, so something with a leaving group? You can probably already tell what's going to happen here, but let's go ahead and write it out, okay? Let's use an acid bromide just to be different for once. So we got acid bromide, and we're going to have our 2-carbon Grignard reagent. It's going to attack the electrophilic carbon, and you always break the pi bond to start, okay? Don't just kick off the leaving group. You could do that if you want to simplify things, but that's not how this actually works. You're going to kick off the pi bond as electrons, and now you have your O minus, you still have your Br, and you have the Grignard that you attached. Now this time, when the pi bond tries to reform, there is a group to kick off, which is the bromine. So now when you do this, you're going to have a reformed ketone, and so far one addition of the Grignard. Now since our Grignard is still present, it's going to attack again because we already established that we can attack ketones and aldehydes, so it's going to do that. And this time, you're going to be stuck as an O minus because you have all carbons surrounding you. So eventually the O minus just becomes an OH, and this is your answer. So this will apply to all the other derivatives, right? If you have something with the leaving group, then you're going to attack twice because the first time you attack, you form a ketone, or I guess like an aldehyde in other cases, and that can already be attacked. So you're going to attack twice. Organolithiums are the exact same, right? Exact same as Grignard. But there is one major difference, okay? I've told this to my students a billion times, and they still forget it. It's okay, I don't blame you. But I want everyone to remember this. Grignards can never, okay, they do not ever attack carboxylic acids specifically. Why is this? A Grignard reagent is very, very, very basic. Yes, we talk about it being nucleophilic, but it's also a very, very, very strong base. Now, when you have a carboxylic acid, yes, this carbon is electrophilic, but look at this. This molecule is literally called an acid. This proton is extremely, extremely acidic, right? I don't know how to write this. I'm trying to get the point across. It's super acidic. The acidity of the proton is way more prominent than the electrophilicity of this carbon. Therefore, your Grignard is going to act as a base. And what is ultimately going to happen here? Instead of you attacking this, this is what you have. This is what you're going to get. This is your answer. O minus. And that's like a stupid answer. It's like a deprotonated carboxylic acid, which can just get protonated later on. And what happens to your Grignard? Your Grignard looks like that. It's an ethane. It's neutral. It's like nothing now. That's what happens when you try to react a carboxylic acid with a Grignard. Super basic. But if you have an organolithium, organolithiums are less basic than your Grignards. Therefore, you can actually attack, okay? So your organolithiums can attack carboxylic acids. However, take a look at this. When you react, your answer will be this. One single addition. Okay? So everything's the exact same. You can attack ketones and aldehydes one time. You can attack carboxylic acid derivatives 2 times. But Grignards cannot attack carboxylic acids themselves. Organolithiums can attack carboxylic acids themselves, but only 1 time. It does not matter if they write excess. You're only going to attack 1 time. Another way they might show this question, they might say carboxylic acid reacting step 1, excess organolithium, and then they'll say H2O, excess. This does not change your answer. The H2O is just a workup step. I'm going to spare you all the details because I don't want to confuse anyone, and you don't have to know the mechanism. If you're curious, just hit me up somewhere. I don't know where you're going to find me, but hit me up at some point down the line. I'll tell you the mechanism. But that's all you're going to get. A 1 single addition for carboxylic acids. Now, if you wanted to react this again, in a separate step, you can re-add your organolithium, and then you can, get your double addition there. But if it's 1 step, and they say excess, does not matter, excess, 1 equivalent, whatever, only 1 time addition. And this happens because the organolithiums are not as basic as the magnesiums or the Grignards. All right, let's move on. So now we're left with this thing, right? This is called an organocuprate or a Gilman reagent. In the context of carbonyls, these are pretty trash. The only thing it can attack is your acid halides. So we'll just use acid chloride. It can only attack acid chlorides, and if you were to react it, it attacks just 1 time. So this would be your answer. And you cannot attack this again. You can't be like, okay, let's attack it again. It's not going to do anything. Organocuprates are very weak for carbon nucleophiles. Therefore, you have to have something super reactive, right? I'm jumping ahead a little bit, but I think a lot of you know acid chlorides are super extremely reactive. So just because they're super reactive, the organocuprate is able to attack it. But if you have anything else, if you had a thioester and you tried to react it with your Gilman reagent, it's not going to react. You have to have an acid halide, so chlorine, bromine, or iodine. So then you're probably wondering, what's the purpose of organocuprates? They're not good for carbonyls. They're good for other things. Like, we talked about this in the last exam review video. Can you do SN2 on an sp2 alkyl halide? The answer is no. You can't just attack it with like that. That's not how that works. You can't do that. But if you have an organocuprate, you can actually attack it. You can like attack this and kick it off. Obviously, there's a different mechanism to this, but it can work. And so you can get that. This is like one of the examples. I'm going to mention organocuprates again much later on. And it will have something to do with its lack of being a strong nucleophile. But just keep in mind, okay, for carbonyls, these are pretty useless. If you're using it in a mechanism or like a synthesis, just what are you doing? Don't use it for synthesis. For carbonyls at least. So I hope this made sense. Please do not attack carboxylic acids with Grignards. Otherwise, I will find you. So we are done with organometallic reagents. Let's move on to fun stuff, okay? Carbonyl reactions. So before we talk about reactions, let's make sure we know what carbonyls are, because these are going to be the things we're reacting with in this section. And we've been using the term carbonyl a lot lately for things that are not carbonyls. So true carbonyls refer to our ketones in aldehydes, which I have drawn right here. Now, a ketone is C-double bond O, in which that carbon is bonded to two R groups, and the R has to be a carbon. And when I say R, I'm just referring to the attachment point. So it's perfectly fine to have something like this and call it a ketone, because the attachment point is a carbon. The moment you change it to something else, like maybe let's say one of them is an H, now you have an aldehyde. If one of them was like a chlorine, you have an acid chloride, and so on, right? So the attachment point has to be a carbon if you want it to be a ketone. For aldehydes, you're going to have an H for sure. The other side, right, this R group, the R can be either carbon or hydrogen. If it's a hydrogen, it's called a formaldehyde. If it's carbon, it's just a regular aldehyde, right? And same deal, we're just talking about the attachment point. Afterwards, you can have whatever you want. So if you wanted this, that's still an aldehyde, right? This is not a carboxylic acid. As far as nomenclature goes, we're not going to really get into it because I don't think they're going to ask you for this on your exam. If you're still curious, you can watch my MCAT video on it. But yeah, I don't think you have to know it for this exam. But we'll talk about a couple common ketones and aldehydes just in case. So for ketones, we have this. This is called acetone. It's your most simple ketone. For anyone who wears nail polish, this will help you. You know, if you want to remove your nail polish, just put a bunch of these mini ketones on your nail and the nail polish will just wash away. For aldehydes, if you have two hydrogens, this is called formaldehyde. Anytime you hear the word form, it usually refers to just one single carbon. This right here, where it's two carbons, is called acetaldehyde. You might have encountered this in your OChem lab, if I'm not mistaken. That's all we're going to talk about for names, just in case they show up. I think formaldehyde, you should, and you know, acid. I mean, honestly, all three of these you should definitely like know. And one more thing before we get into reactions is reactivity. So in general, aldehydes are more reactive than ketones. I'm saying in general because there are instances where that's not the case. But if you're comparing two equivalent ketones and aldehydes, then your aldehydes will usually be more reactive. Now, why is this? Let's take this C-double bond O right here, right? There's going to be a dipole moment going upwards, which means that your carbon is partial positive, okay? And because it's partial positive, it's going to be electrophilic. If you can stabilize this partial positive charge, it's not going to be as electrophilic. If you can destabilize it, you might become more electrophilic, because electrophilic means it's dying for electrons, it's dying to be reacted with. So if we look at a ketone and we compare it to an aldehyde, okay, we got a partial positive right here and a partial positive right here. What is our ketone bonded to? We have two alkyl groups, in this case methyl, and alkyl groups are going to be electron donating groups. So if you think about it, you're donating electron density. And I hesitate to use the word neutralize because that's not what's happening here, but it's a way to think about it. You can think of it as like the positive is being neutralized by the negative, right? It's just, in reality, it's just being stabilized. But since this is having 2 electron donating groups, we can kind of use that as a comparison factor to our aldehydes. If you look at our aldehyde, it only has 1 electron donating group. So which one has more stability or more stabilizing effects? It's going to be the ketone because it has 2 donating groups as opposed to 1. Therefore, the aldehyde is going to be a little bit more partial positive than the ketone, which means if you have an instance where you have one molecule that has 2 carbonyls and they say react with 1 equivalent of a Grignard, you're going to react with the more reactive one, which is the aldehyde. So in this case, your answer would be that, because our ketone is not as reactive as the aldehyde. So that's a general rule of thumb. Right? Aldehydes are more reactive because there's less stabilizing effects. If I brought in a formaldehyde, this formaldehyde will probably be more reactive than this acid aldehyde, because in this case we have no electron donating groups. You might be thinking further, what could be more reactive than this? Something with electron withdrawing groups. This is where a ketone could end up being more reactive than your aldehyde. So if you have, let's say you have a ketone and you're just bonded to a bunch of these fluorines. This is not the best example. I'm not going to elaborate why, but pretend side reactions don't occur here. But let's say you have super strong electron withdrawing groups like this. What is going on? You have electron withdrawing groups, which is actually going to do the opposite, right? It's going to take away negative from something that's not even negative. How can you take away a negative from something that's positive? All that's going to do is make this even more positive, which means it ends up being more reactive. Once again, it's not the best example, but I'm just giving you like a little example here, just to make a point. So that's kind of what you want to think about. And we'll talk about later on, how do you react with the less reactive one? But for now, just know that aldehydes are generally more reactive than ketones because they have less stabilizing effects. So if we want to react with carbonyls, we should first know how to make them. So we're going to talk about synthesis of carbonyls. A lot of these reactions are going to be a blast from the past. They're going to be repeats from stuff that you already know. So we'll go ahead and start with alcohols. If you have a primary alcohol, remember that you have to use something mild. So PCC, right? All the acronym ones, PCC, PDC, DMSO, SWERN, etc. You have a bunch of options. Just if you're using something with an acronym or a name, it's going to be mild, and mild will lead to an aldehyde. If you use something strong like chromic acid, it's going to turn it into a carboxylic acid. So you don't want to do that, for primary at least. Now, what if you have a secondary alcohol? So we'll do that. Over here, it doesn't matter if you use mild or strong. And to give you some examples, right, chromic acid, KMNO4, dichromate, etc. These are all going to make just a ketone because you can't oxidize this further. All right. What else can we do? We can do oxidative cleavage. So let's take a alkene. And if we want to make ketones and aldehydes, you have to react with reductive ozonolysis. So that's going to be ozone with DMS or ZN. And what does that do? Split it, separate, and just attach O's in place of the double bond. So you got, in this case, you made both an aldehyde and a ketone. Make sure to write DMS or ZN because it could be assumed that you're in different conditions, and ozonolysis can make carboxylic acids. But if you specify DMS or ZN, it will mean that you're only going to make the aldehyde and ketone maximum. So that's something you can do. Make sure you don't use something like K-4, hot and concentrated, because that's going to make carboxylic acids if there's an H present. Now, if you had something like this, technically you can use KMnO4 because you can't oxidize this past a ketone. So if you were to separate it and you put your O's on there, there's nowhere to put an OH. You can't just kick off the carbon. But in general, right, if you're trying to make ketones and aldehydes, just use O3. It'll save you from any unwanted errors, okay? So O3, DMS, and zinc. That's another way we can make ketones and aldehydes. And I guess to specify, you cannot make aldehydes out of KMnO4. You'd have to use O3. KMnO4 can make ketones, but not aldehydes. Okay. What else can we do? We can do something from last exam. We can add carbonyls to a benzene. So remember Friedel-Crafts acylation. I'm not going to go over the mechanism because we already went over this in the past and it's not too important for this exam. But you're going to attach from the carbon that's bonded to the chlorine, or the carbonyl carbon. So carbon 1, carbon 2, you're going to attach from carbon 1 like always. So you have your benzene and you're going to 1, 2, right? Carbon 1 has the carbonyl, so your carbonyl is there. Once again, don't forget all the little intricate details about like orthoparameta. That's stuff from the previous exam. We're not going to go over it now because it's going to take way too long to go over everything, right? That's why we have the old exam videos available. But that's what happens there. Let's use a different number of carbons. So let's do that. Once again, you're attaching from the carbonyl carbon, so we can number it 1, 2, 3, 4, 5. And in your answer, you got your benzene, and you're going to draw 1, 2, 3, 4, 5, and your carbon 1 always has the carbonyl. So that's like another way in which you can, synthesize a carbonyl. In this case, on a benzene. Something else we can do is carboxylic acid. I'm going to give you 5 seconds to tell me what to do here. 5, 4, 3, 1. You have to use organolithium here. You can't use Grignard. You can't use organocuprate. Organolithium, because remember, it's only going to attack once. And by the way, it can actually attack, whereas Grignards cannot attack. So when you do this, you're going to keep that other side the same, but then the OH turns into the organolithium. So you get that ketone. And once again, it doesn't matter if they write excess and H2O. It just means the same thing. The H2O is a workup step. You still get the same answer. And excess doesn't change anything here. All right. Let's talk about alkynes. So you can do both ketones and aldehydes. I mean, obviously it depends. Like in this case, since we have a terminal alkyne, we can make an aldehyde. If you had an internal one like this, you can only make ketones because the double bond O goes on one of these carbons. So if you want it to be an aldehyde, it has to be at the end. To make a ketone, we're going to do the Markovnikov version, right? If you guys remember from alkene or even alkyne, to be honest, because you guys have done this before, it's going to be the mercury reagents, right? The mercury reagents do the Markovnikov, whereas anti-Markovnikov involves like a boron. So for Markovnikov, we're going to use HgSO4, H2SO4, H2O. And keep track of the number of carbons you have. You have 3 carbons, right? So 1, 2, 3. It's going to be on the second carbon, right? This is carbon 1, 2, 3. Because we're putting it on the alkyne carbon. So you got that. For anti-Markovnikov, it's going to be the boron one, right? So usually they use Ca2BH, and then you got your H2O2 NaOH. They could throw in a little THF over there for the vibes. But the Cia doesn't have to be Cia. It can be any R group. So it could be, they could write it like this. CH3, 2BH, right? Just make sure you recognize it. This is going to be anti-Markovnikov. So when we draw the 1, 2, 3, the 3 carbon is where you get your double bond O. So in this case, we made an aldehyde. Now, I need to talk about something, which is going to be keto-enol tautomerism. If you're in Pan's class, I would definitely recommend knowing this because he is obsessed with these. Technically, what you make in both of these reactions at first is going to be an enol. So you make that, which becomes the ketone. In this case, you get that, which becomes the aldehyde. Don't worry. All I'm going to tell you is if you ever, no matter what the reaction is, if you ever make something like this, just turn it into the carbonyl form. How do you know what you're looking at? This is called an enol. Okay, it's an alkene plus an alcohol. And they have to be on the same carbon, right? So as you can see, one of the carbons on the alkene is the carbon for the alcohol. If you had a situation like this, this is not an enol because neither of these carbons are bonded to the alcohol. So that would not be an enol. But this, what I drew, is an enol. Anytime you force something like this, just turn it into a carbonyl and remove the alkene double bonds. So in this case, in red, that's what we normally or technically get, but it tautomerizes into the orange compounds. And we're going to talk about how this works. Once again, if you're in Pan's class, I would pay extra attention. This is one of those mechanisms that could show up on your exam, right? They're going to ask you at least 1 or 2 mechanisms, so this could be one of them. We're going to talk about both types of tautomerisms. So first, we're going to talk about base catalyzed tautomerism. And keep in mind, you can go backwards, right? You can go from red to orange or orange to red. So we're going to go both directions and both conditions. So base catalyzed, let's go ahead and start with our ketone. You're in basic conditions, so you're going to have a base present, and the base is going to extract one of your alpha hydrogens. So you're going to take this and form like a negative right there. So you're going to get a deprotonated ketone. Now you can do a little resonance action right here. Right? Anytime I see a resonance opportunity, I just do it. That's how I remember this stuff. Just do it, because what else are you going to do? So when you do that, you formed your little enolate thing, right? And remember this OH from the beginning? It extracted a proton, making it into a water. So you still have that water present, and the water is going to act as an acid and give a proton to the orange oxygen. And when you do that, what did you form? You successfully formed your enol, and this purple thing became a negative OH, which might make you think, okay, can I just go backwards? And that is the case, right? Because, after you do this, you keep forming a base, it will just go backwards and it'll go forwards again and backwards and blah, blah, blah. That's what an equilibrium is about. You can go from one thing to the other or the other thing to the first thing, back and forth, but there's an equilibrium constant in which one of them is more favored. As I mentioned, the keto is the favored form, but just forget that for now. We're going to talk about how to go backwards. So we just formed this enol. Now let's say that it wanted to go back into a keto. What are we going to do? So we have our hydroxide present, and it's going to deprotonate, right? It's going to deprotonate this, kick that up into electrons. So then we're going to get O minus. I see a resonance opportunity, so I'm going to do it. Resonance, kick this up. What am I going to get? Double bond O, negative carbon. This brown beige OH became a water molecule, so it's going to one second, let me draw this better. It's going to donate the proton. And ultimately, you turn back into that ketone. And as I just mentioned, you reform this thing. So that's why sometimes you'll see it written like this. You'll see an OH, they'll draw an arrow to the ketone, and there will also be a backwards arrow. But notice how the forward arrow is bigger than the backwards one. That means that this is favored. So anytime you have an enol, just turn it into a ketone, or an aldehyde if it's an aldehyde. Okay, so this was base catalyzed. Now we're going to talk about acid catalyzed. By the way, if I haven't mentioned it already, I would recommend writing mechanisms whenever I write them. If you just verbally watch, you're not going to be able to replicate it, for most of y'all at least. So let's talk about acid catalyzed. I like base catalyzed way better, but we're going to do acid anyways because I think it showed up on last year's final or something. So yeah, start with the ketone. Acid catalyzed means you have protons floating around, so H plus H2O. So you're going to bond, right? Because your oxygen has electrons, so it can act as a base and take the proton. When you do that, you're going to get an OH plus. And then I see a resonance opportunity, so I'm going to go ahead and do that. I'm going to kick this pi bond up and get myself a little positive right there. Okay, now what do? I have H2O present, and I have an alpha hydrogen right here. What I'm thinking is if this oxygen were to bind to this H, I'll form a negative right here, right? Which can then resonate. And so that's exactly what happens. You bond to the H, and this pi bond, well, it becomes a pi bond, right? That sigma bond between the H and the carbon breaks off and forms this. And as you can see, it would satisfy this charge right here. And so that's what happens. So now you just formed your enol because you have that double bond right there. So that's how acid catalyzed works for keto to enol. And if we want to go backwards, same deal, right? We're going to have H plus present. Now you have a double bond, right? The double bond is going to act like a little nucleophile, if you want to call it that, and it's going to bond to the H plus. One of the carbons will do it, and it's going to be this right carbon. It's going to bond to the H, and I'll tell you why that happens in a second. Take a look. You form a carbocation in the middle that's resonance stabilized by the OH. If you said, let's do it in pink, if you said that this pink carbon bonded, you would end up with the carbocation that's primary and it's not resonance stabilized. That's why the purple one is the correct answer. Okay. Now from here, I see a resonance opportunity, so I'm going to go ahead and do that. Resonate here. You turn to an OH plus. And ultimately, water molecule will extract this proton, break that bond to the O, and make your keto. So yeah, that's how tautomerism works. There is another type of tautomerism, which we'll explore in the amines chapter, but it's going to be imine to enamine. But as you can see, it's like the same thing. It's just you have an N instead of an O. So if you understand this, you can understand the other one. Sounds good? All right. More synthesis stuff. So we can also reduce into aldehydes. We talked about oxidizing right now, but we're going to talk about reduction. So guys, normally, if you have something like this, like a carboxylic acid, and you use a reducing agent strong enough to reduce the carboxylic acid, such as LAH, it just becomes an alcohol. If you used NaBH4, which is weak or mild, it's not going to do anything. So this is what we were taught. But there is a way to partially reduce into an aldehyde. And that's going to be via the usage of bulky reducing agents. So one of the common ones that you'll encounter, first of all, LAH, by the way, is LiAlH4. Okay, so this is what they did. LiAl, 3 of the H's became like a tert butoxide type thing, right? So it's gonna look like OT, Bu3, and then H. Right? Normally the Al is bonded to like 4 of these H's, but now 3 of them are huge. Like this type of thing, right? So it's bulky. As you can imagine, being bulky affects things. So what is this going to do? It's still strong because you have your aluminum, which has weak bonds to H, which means that the H is going to become a hydride and attack. But because it's bulky, it's going to hinder it a little bit, meaning that at most, you're going to make an aldehyde. Okay? Another bulky reducing agent you could use is dibol H. Dibol H is diisobutyl aluminum. Right? Isobutyl looks like this. Right? It's big. Well, hold on. Like that. Like you're bonded to this carbon. But that's what an isobutyl is. It's bulky. There's 2 of them. So as you can imagine, it's going to do the same thing. And it's going to turn into an aldehyde. So make sure you know this. Now the good thing to know is like pretty much anytime you use dibol, you're going to make an aldehyde. So if you used an acid chloride, if you use, the carboxylic acid that we just talked about, ester, even a nitrile, all of these, right? If you used all of these and reacted with dibol H, you just get an aldehyde. Obviously, make sure you're counting your carbons, but like I specify that for this because people forget that this is a carbon. But since we have 2 carbons, right, 1 and 2, we're gonna have a 2-carbon aldehyde. So yeah, that's what you'd get. And don't forget, if you were to use even like an ester and you used LAH, it would just become an alcohol, which is why you need dibol if you want to make the carbonyl. All right, let's move on. So we kind of already talked about this, but we're going to talk about it again just because it's fitting for this chapter. But it's going to be turning acid chlorides into ketones and aldehydes. Okay, so the first one we literally just talked about, but I'll mention it again just for organizational purposes. But if you use LiAlOT-Bu-3H or just dibol H, you're going to turn it into an aldehyde. So there is that. Another thing you could do, let's say you want to make it into a ketone, we talked about this in the very beginning, is using your organocuprates or your Gilman reagents. So if you used R2Li, you're going to get a 1 attack of your R2. So you'll get this. To give you a specific example, we'll use an ethyl. You know what? Let's make it a propyl to switch it up for once. So you're going to keep this side the same. The chlorine gets replaced by the purple group. So 1, 2, 3. So you made your ketone. And remember, if you want to keep this ketone, you have to use the CuLi, because the moment you use the other ones, like let's say you used a Grignard, it's just going to attach it twice and you get an alcohol, which is not what we want. And you can't just say, oh, I'll oxidize this, because you cannot oxidize tertiary oxygens. At least that's not what y'all think. There actually is a way, but we're not going to talk about that because it's way out of the scope. But you can't do this, right? It's not going to lead to anything. Same thing would happen if you used organolithium. It's just not working, okay? So you have to use CuLi. All right, let's move on. We just talked, see, I swear like a lot of these are repeating, but I guess like if I repeat it, it will get the point across more. But I don't even know what to classify this. I don't know. I mean, it's like a mix of things, right? I'm just like putting 3 types of reactions together. It's just like nucleophilic attacks, basically. So if you have a carbonyl, oh, by the way, guys, I'm stupid. Okay, we're done talking about synthesis. Now we're going to talk about how to react carbonyls. Okay, I'm just going to not classify this first one. Okay, the first one is going to be Grignard, right? So if you have a carbonyl and you're reacting with a Grignard, what is going to happen? You got your Grignard right here. Carbon tax kicks up. And what do you get? An O minus. You still have your other carbon. And you just attached a new one. Because there's no leaving group to kick off, your H plus will come in and protonate. And your ultimate answer is a tertiary alcohol. But if I have a ketone and I'm reacting with LiAlH4, I don't know if I've ever mentioned this in the past, but like the way it works is you have an H minus, so it's kind of like a Grignard, but like it attacks and stuff like that, right? And like, I mean, think about it. When you do that, what's gonna happen? You have 1, 2, you just have an H that you added, and then you have your O minus. Can this reform and kick off anything? It cannot. Therefore, it ultimately gets protonated. But you know, I don't like writing hydrogen, so I'm gonna write it again. So you get this. But that's what a hydrate is, an H minus. And lastly, for this little category of miscellaneous, if you were to use H plus H2O, think about what happens here. I want you to kind of like logic it out. The first thing that happens is we have our H plus, right? So our H plus, by the way, this is not the tautomerism thing, it's a different reaction. So if you have H plus, this will become protonated. And let's go ahead and bring in our H2O. The H2O is going to attack this carbon and kick the bond up. And as a result, you got your OH there, and you have your water that you just attached. And through a workup step, you're going to just end up with 2 OHs. This is called a geminal diol. Guys, I think I have like short-term memory loss or something. So I don't know if I already mentioned this, but like this reaction is like kind of whack because anytime you form a geminal diol, it's just going to turn itself back into a ketone or an aldehyde because geminal diols are very unstable. It's not good to have 2 OHs on the same carbon. So it just like reverses itself. It literally, you know, there's protons present, right? So the proton will protonate one of these. You turn it into a water, and then you just reverse it, right? You attack, you kick this off, and you end up with that. Something like that, right? Which becomes your ketone. So like, I mean, if they told you to react this ketone with acidic water, just turn it into this little geminal diol. So like your official answer would be this. But I highly doubt you're going to give this to because it's like really unstable. The one carbonyl that actually is stable like that will be like an aldehyde. So if you had an aldehyde and you reacted with H plus H2O, it actually would prefer to turn into a geminal diol. But usually that's not the case. Anyways, good thing is they don't really care about these little details. They're not going to try to confuse you. We're just going over it right now. All right. Now let's talk about something called cyanohydrins. So cyanohydrin is going to be, take a carbonyl and you're going to react it with Cn minus. So this kind of goes back to what I talked about before, right? I mean, these are all similar, right? You have a carbonyl, which is an electrophile, and you have a nucleophile. So nucleophile is attracted to the carbonyl carbon. You always kick up the pi bond no matter what you have. And as a result, you're going to get an O minus and a Cn. And there's nothing to kick off, so the O minus just becomes an OH. That's what a cyanohydrin is. Now, there is something else you can do. We have not talked about this yet because this is going to be in the carboxylic acid chapter. But if you were to react with acidic water, you can actually turn this Cn into a carboxylic acid. I'm just mentioning it here. just to be a little extra, but we'll talk about it again when we get there. But you can turn this into a carboxylic acid. So you can make something like that. By the way, this is like a type of an amino acid derivative. It's not an amino acid, but it's like a way to make a derivative of it. So there is that. Let's talk about imines and enamines now. So you got imine and enamines. So an imine is when you have a double bonded amine, right? A normal amine looks like this, right? Single bond NH2, but an imine is when you're double bonded to the N. Anytime you hear the word im, it just means that there's like another bond to a nitrogen. For example, if y'all had this molecule, this is called a pyridine, right? Pyridine. There's something called a pyrimidine, which if y'all know biology, you guys know about your nucleotide bases, right? You got cytosine, thymine, these are your pyrimidines. And the pyrimidines are going to have this type of a structure, where you have two nitrogens, right? So pyrimidine, right? When I see the im, it tells me that it's a pyridine, but with an extra N. So if you guys look at imine, it kind of sounds like there was an amine, but with an extra N. That's how I remember that this is going to be what an imine is. So imine is that. Now enamine, I want y'all to sound it out. It's just like enol, but it's en and then amine. So an enol looks like this. Just replace the OH with an N. So you're going to get like NH2. By the way, H and like carbon can be used interchangeably. Like I can call this an enamine, and I can call this, oh my god guys, I'm stupid. I can call this an imine, and I can call this an enamine. That's fine. As long as there's like a nitrogen in the position we want it to be. So why are we talking about these? Because we can turn carbonyls into these. So let me write these again. The shortcut here is if you have a primary amine plus carbonyl, you know what? Let's just draw it. Primary amine plus carbonyl equals an imine. Secondary amine plus carbonyl equals enamine. And tertiary does not work here. Make sure you know what primary and secondary mean. So primary just means number of carbons you're bonded to. So this would be primary amine because the N is bonded to one carbon group. If I had this, the N is bonded to two carbon groups, so that's going to be secondary. And then if I had triethylamine bonded to three, so this would be tertiary. So I'll go over the mechanism in a second, but let me give you some examples. Let's say I had this carbonyl, and I'm reacting it with that. My answer would be an imine, because I just said that. And look what stays. It's the carbon group that stays. What if I had this, and I'm reacting it with a secondary? I'm going to turn it into an enamine. So it's going to look like this. Once again, notice how it's the carbons that are staying. Now, how do I remember which one makes an imine and which makes an enamine without knowing the mechanism? You just look at like how many carbon groups there are on the amine. What do I mean by this? The first thing I would do is just draw a single bond to an N and keep all your carbons the same. So for this top one, we have just one carbon on the N. So I'm going to draw a carbon on the N. Now the question is, can this N afford another bond? The answer is yes, because amines, or just nitrogens, they can take 3 bonds total. So that third bond will become a pi bond, and I make an imine. What about for this secondary one? Same deal. I'm going to replace the double bond O with just a single bond to an N, and I'm going to keep all the carbons. I don't really care about the H because the H is able to just be protonated and deprotonated, right? You can just remove it. Question, can the N afford another bond? The answer is no, because the N already has 3 bonds. So that's what's going to tell me that you make an enamine, and you put a double bond there. Now, keep in mind, if you have like an asymmetrical carbonyl and you're reacting with your secondary amine, you're going to turn it into an enamine, but the double bond goes on the least substituted position. We'll talk about why in a second, right? I keep saying we'll talk about why, but I'm going over all the little tricks and stuff to remember before going over the mechanism. So it's going to go there. All right. Now we're going to talk about mechanisms here. You got your ketone, and we got our primary amine. So the first step, right? I mean, sometimes they'll give you protons, sometimes they won't. But the first thing we can do is just say that the O gets protonated. So we're going to get like an OH plus. Now guys, I probably mentioned this. See, like, I'm just mentioning it again because I don't know who's going to like watch this, but like, or watch like the old stuff. But anytime your O gets protonated and it's like positive, that really, really weakens this bond, which means it's extra reactive because the O is dying to take some electrons, okay? Just keep that in mind. So anyways, your N is going to come in as a nucleophile, strong one by the way. It's going to kick up that pi bond. Now when you do it, you got your OH and you have your amine that you just added. Now the amine is going to be positive because it has too many bonds. And so you're going to do what's called a proton shift or a proton transfer. This is a common thing you're going to see amongst mechanisms where they write the word PS. It just means you're moving protons around. So I'm going to draw this in pink. Technically what happens is you're going to have like a water molecule present in the solution, and it's just going to take this pink proton to become like a hydronium ion, and then you just donate it somewhere else. You know what I'm saying? But because it's too much work to write the water coming in, taking something, removing it, blah, 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 we just write PS and we kind of understand what's going on. So essentially, the pink hydrogen gets removed from the nitrogen and it gets placed onto the O and it becomes positive. Now, why does this occur? Because we're trying to remove the O, so we have to make it a leaving group, and we're trying to keep the N, so it should like try not to be positively charged, otherwise it's its own leaving group. So you make this right here. I'm gonna rewrite it because it probably looks confusing as hell. We got our water molecule. All right. Now the N is going to form a pi bond and it's going to kick off the water molecule because it's a leaving group. Now when you do that, you got your double bond N, and of course it still has an H bonded to it, making it positive. Ultimately, you're going to do a workup step, right? So you just lose the proton, do a workup step, right? So some base will come in and take it, and you end up with your imine. So that is how a primary works. Now we're going to talk about secondary, and we're going to use an asymmetrical one. So you got your secondary amine, and sure, we'll add acid again. So the first thing, as usual, is the O gets protonated. Once again, it doesn't, like, it's not the end of the world if it doesn't, but we're just going to do the protonated version. And your N is going to come in, attack the carbon, and kick up the pi bond. Next, you got your OH, and now you have your N with 2 carbons, and we got our pink hydrogen. Same exact deal, right? Right? The beginning is the same. You got the attack, you got the protonation, the attack, you got the proton shift. So now the water, or the O, is going to become a leaving group because it's going to have OH2. And you have your neutral amine attached. Same deal. Your N is going to reform just form a pi bond and kick off the water. Now take a look at this. This is where things are a little different. You basically made an imine. Well, this is called an iminium because it's positively charged. But you made an imine, and you can't just say, I'm going to lose a proton and neutralize myself like we did over here, because there is no proton to lose. So this is where you're going to do a little bit of some tautomerisms, okay? So here's what's going to happen. You have some alpha hydrogens present, and as you might be able to tell, you're going to like try to form a negative here and do some resonance action, right? But let me take it a little slower. You have 2 protons present. A base will come in, and it's going to extract one of these hydrogens. The one it extracts is the one that's least substituted, just because acidity, right? When you look at acidity, you leave a negative charge, and negative charges are more stable on primaries as opposed to secondary and tertiary positions. So this left hydrogen is going to be more acidic than the right one. So this base will take the proton and kick off these electrons as a bond and shift this upwards. If that made no sense, I'll do it in a simpler manner. You're going to take this proton and turn it into a negative charge. Okay, now you can do some resonance here. So you form a pi bond and you kick this up. And what do you end up with? An enamine. So that's why we create an enamine here and not an imine. And this is also why our double bond is on the least substituted position, because the H that ends up leaving to form this pi bond is the more acidic one. Now, if you're wondering why tertiary cannot react, take a look at this. If your tertiary amine reacted, you would have this right here. Do you see how there's no way a proton shift can occur because there's no protons in the N? So if you had a tertiary amine and it reacted, it would probably do this, but then the O would be like, nah, and then just kick it back off, and you'd end up with your ketone again. So yeah, that is how amines and enamines work. Or that's how you make them. All right. Let's go and get rid of all this. I guess very briefly, we'll talk about amine, enamine tautomerisms, but we kind of already just talked about it, but we'll do it again, just in case, right? So if you were to do base catalyzed tautomerism, what are you going to do here? You take the most acidic proton, so it's going to be this one. So you take it and you move the electrons around, and you end up with an N negative. Now this thing became a water molecule, so the water is going to donate a proton, and you just established your enamine right here. If you want to go backwards, no worries, right? You got your base, takes a proton and makes it into a negative N. Then you do some resonance. You got your negative right there. And then you're going to have a water present to give a proton, and you're done. So it's the same thing as keto-enol. It's just you have an N present. It's nothing crazy. All right, let's move on. Now we're going to talk about nitriles a little bit. So nitriles are going to be CN. So we got this. But I'm going to write it like that. Something to keep in mind is nitriles are also very electrophilic. Why? You have a dipole moment going towards the end, and so the carbon is going to be partial positive. It's just like your carbonyls. Now, here is the thing. If you react this with something like, let's say a Grignard, let's do that. You can react, and what's going to happen? You break off one bond. Now, what do you get? C, double bond N, and we have our Grignard right there. Now our N is going to be negative. And how do you protonate it? By using like H plus H2O. And so you get that. But I want to tell you something, which is that if you have like a water or even like acidic water and you have an amine, it ultimately becomes a carbonyl. So in the past, like, right before this, we talked about how to go from here to that. But you can also go backwards, and to go backwards, you use H plus H2O. I believe this is in the amine chapter, so I'm not going to talk about it right now, but you can go backwards if you just use H plus H2O. And so since you have to use H plus H2O to neutralize the N, when you do this, when you make the NH, your H2O is going to do whatever it does, right, and attack, and you ultimately end up with a carbonyl. So don't worry, guys, if this was confusing. All I'm going to tell you is anytime CN reacts with Grignard, you're going to get a carbonyl. Let's do a couple more examples so y'all don't get confused. Let's do that. What am I doing, guys? Let's do that. Okay. If I'm reacting with, let's do a 4-carbon Grignard. Just pay attention to the number of carbons you have, right? So keep everything the exact same. Let's draw our little cyclohexane. We'll draw a little ethyl group. Now, remember, okay, this carbon is going to be the carbonyl carbon of your ketone. So this is the same one. Make sure you remember that so you don't add or lose any carbons, right? This is the C that becomes the double bond O, and you just attach this Grignard to it. So you're going to get 1, 2, 3, 4. If you want to draw it in a better manner, you can just draw it like that. That's your answer. All right. One more thing with regards to nitriles is, don't forget, you can reduce them with a dibol. So if you use dibol or even the other one, the LiAlOT-BuH, you're going to get an aldehyde, right? As I keep mentioning, anytime you use dibol, you're just going to get an aldehyde. So the biggest thing that I can say about nitriles is please keep track of your carbons. They usually write it like this, where they keep the other carbons as vertices, and then this carbon, they write it out. So people tend to forget that this is a whole carbon. But if you number it, you have 4 carbons. So your resulting product should have 4 carbons. And that 4th carbon is the carbonyl carbon. That is the result, right? So you're going to get this as your answer. Okay. Next up is the Wittig reaction. I have a lot to say about this. First, we're going to talk about just the reaction itself. It's a very fun reaction. So you're going to have a carbonyl, and you'll get something like this. PH3P, double bond, that. The simple answer is whatever your P is bonded to, it's going to replace the O entirely. So I like to draw a little box And I'm like, okay, I'm going to attach this thing in place of the O. And of course, this is the attachment point, okay? So if you had something like this, you attach it from this green arrow. But let me erase that. So we're attaching 2 carbons. That's all we're doing. We're going to replace this and attach like an ethyl. So what's that going to look like? Heat the double bond, and it's 2 carbons, so that's your answer. If I gave you this, what is my P double bonded to? That. Like, literally just replace the O with whatever's in the box. Like, you don't even have to write, like, carbon or anything. Just, like, do this. That's your answer. Of course, I don't know why, but some people think that you're replacing the O with nothing. This is a whole carbon, guys. It's a whole carbon. But you can leave it like this because it means there's a carbon right there. But that's your answer. Such a fun reaction. Now, of course, I have to, like, mention a couple things. They might write it differently. They might write the reaction like that. If they do this, just don't panic. You know that the answer is going to be the O being replaced by whatever the P is bonded to. So just same deal, draw a little box. Whatever is in this box, draw that atom. Forget the charges, just draw the atom. So you have a double bond, and what atom is there? It's just a carbon. So you leave it like this. There's like a carbon. If they gave you PH3P, that, same deal. Draw a little box right here. Forget this negative and attach this group in place of the O. So your answer would be now let's talk about some more stuff, like how does this get produced. We'll talk about, I don't know, like mechanisms and stuff like that. So first, you'd start with an alkyl halide, and then you react it with PPH3. pH is going to be your benzene rings, so technically a PPH3 looks like this. Okay. But don't forget, the P is a nucleophile because it has electrons. It's a bulky one, but still a nucleophile. It is important to know that it's bulky for reasons I'll mention later. But you attack this carbon and you kick this bromine off, and then you get this structure. Okay, you have a carbon. It's bonded to the PPH3, but do you guys notice how the PPH3 was neutral? So if it formed an extra bond, that means it's going to be positively charged. This is what's called a phosphonium salt. Now, next, you can use a reagent called Bewley. It's just a butane with a lithium. Bewley looks like that. And essentially, this is negative, right? It's a very strong base. And so the strong base is going to deprotonate this carbon right here. And you end up making that. This is called a phosphorus ylide. Technically it's pronounced ylide, but I don't like that, so I call it ylide. An ylide is any time you have like a carbon that's bonded to another atom. So we'll put the letter, I don't know, I'll put like a question mark here. Okay, so you have like a negative carbon and a positive heteroatom right next to each other. That's what an ylide is. This is called a phosphorus ylide because it's a phosphorus as the heteroatom, but it's an ylide because we have a carbon and another atom, negative and a plus, right next to each other. If you had something like this, this would be called a nitrogen ylide. So you're going to make this phosphorus ylide, and a resonance form of this is to just bring this negative down. And that would look like that. Do you see how like there's no charges or anything? Which is why when I mention like, you know, if they gave you this or if they gave you that, the answer is like the same thing, because you're reacting with the same thing in this case. They're just resonance forms of each other. So for this top one, if I said to attach this thing, then the same thing can apply over here. Just attach this thing, right? They're the exact same thing. They're both called phosphorus ylides. So yeah, just know that. Bring out this little resonance structure, and then yeah, if you react with a carbonyl, whatever is double bonded to the P will replace it. So you're gonna attach that. Let's talk about mechanism. It's really not that bad. People were complaining about it when they first heard about it, but it's really not that bad. So you got this, and we're going to have, let's write the pH3 right here, and we'll do double bonded CH2. So the carbon, right, we already established that the carbon is partial negative and the P is partial positive. So I'm going to keep this here. What about over here? What is partial what? The carbon is partial positive, whereas the O is partial negative. So do you see how this will be attracted to each other and these will be attracted to each other? That's what's happening. That's why I oriented the molecules like this. So your carbon is going to use this pi bond to bond to the electrophilic carbon. Now the oxygen is going to use its pi bond to bond to the P. And when you do this, look at what you get. You get this cool looking intermediate. So you're going to have single bond O, and the O is bonded to the P, and the P is still bonded to the CH2, and the C just formed a bond over there. Y'all see that? Now, what happens afterwards? Oh, by the way, guys, I was like tweaking for a second because I was trying to remember. I think I got asked to draw this intermediate on my final from 2 years ago, I think. Anyways, this carbon is going to do the exact same thing. It's going to take its bond, form another bond. The oxygen will do the exact same thing. Take its bond and form another bond. Do you guys see that? We just did this thing twice. The carbon essentially used both of these to bond to that one, and the oxygen used both of these to bond to the P. It's just like it happens one at a time. So your ultimate product is going to be this. So you have your carbon here. You see this CH2, it formed two bonds, right? So you form two bonds to the CH2, and what happens to the oxygen? The O just basically formed two bonds to the P. So you get like that. But yeah, that's what you get. So now, let's talk about one more thing with regards to this. They might give you a little product, and they'll be like, can you show how you made this via a Wittig reaction? So here's how you approach it, okay? Wherever you see the double bond, just split it, and know that one side will be the carbonyl, one side will be the Wittig reagent. So for example, let's just first split it, okay? So we have this, and we have that. You could claim that this was the carbonyl and that this was the Wittig, or you could flip it. You could say that this was the Wittig and the right side was the carbonyl. I mean, if you reacted both of these with each other, you would get the same result, which is that. But there is a better answer here. The better answer would be this one. And it just goes back to how the Wittig was created. So remember what we said? To make a Wittig, you're going to start with an alkyl halide. So you would have that as your alkyl halide. Let me draw it the other way so it's easier to follow. If you reacted this with PPH3, you get your thing right here, right? But remember what I said about PPH3. It's very bulky. So the less sterics you have to deal with, the better. What is our alkyl halide? It's a primary alkyl halide. That's very good for SN2, especially when we're dealing with bulky things. But what about this Wittig reagent? How did we make that? We made it through a secondary alkyl halide. So PPH3 reacting replace, and this is a secondary alkyl halide. It's still feasible, but if they ask for the best option, you would take the one in which the SN2 was less hindered. Okay, so yeah, we established that the better option is the above reaction. So now they might ask you to draw the whole pathway. So the first step would be, you got your alkyl halide. So this is your alkyl halide. Next would be an SN2 with PPH3, and that's going to give you what's called your, it's just like a phosphonium salt. It's forming a salt with the Br, right? Don't worry about this. It's just negative and a plus together, but that's what it's called. Salt is when you have one charge on the molecule, because it's going to form a salt with like another ion. Anyways, after this, what do? You use Bewley. Bewley is very, very strong base. I wouldn't just use random bases like OH, just use Bewley. Bewley is going to deprotonate this carbon, and that's going to make your actual ylide. So you get that. This is called phosphorus ylide. And a resonance form is that, right? These are the same thing. Then you react this with your carbonyl, which we decided is going to be acetone, and you just replace this O with whatever is bonded to the P. So then you get your answer, which would be that. All right. So I mention all this because, yeah, like sometimes I've seen them write the reaction where they'll give you this, and then they'll be like step 1, Bewley, step 2, that. And some people tweak out about what Bewley is. Bewley just turns this into an actual Wittig reagent, right? So step 1 would create that, and then step 2 is just replace. So your answer would be that, because we're attaching this thing. I hope that made sense, because now we're going to move on. All right, guys, let's talk about protecting groups. So in the past, we talked about how to protect alcohols. We said to use TIPS chloride, and that protects your O. And then if you want to deprotect it, you use TBAF, right? And that makes it back into an OH. So that was for alcohols, but now we're dealing with carbonyls, so sometimes we need to protect carbonyls. And I want y'all to tell me, when will we need to protect a carbonyl? If you look back at what I said, you remember that aldehydes are generally more reactive than ketones. So if there's ever an instance in which we want to react with the ketone and not the aldehyde, it's going to be hard, right? Let's say that we wanted to make this product where we reduce the ketone but not the aldehyde. Well, if you use LAH, first of all, if it's excess, both will be reduced. But if you were to do one equivalent of LAH, the one that's more reactive is the one that gets reacted with. So it would be the aldehyde. You don't get the product that you want. So you have to protect it so that you can prevent it from reacting. So you're going to use a glycol, or this vicinaldiol, and of course you can specify one equivalent. And the way this works, I'm not going to go over the full mechanism because I think it's very similar to things we've done in the past, and I actually encourage y'all to attempt it on your own. But like essentially what happens is the O from the glycol will attack this carbon, and you break this bond up. And, ultimately, without getting into too much detail, you're trying to remove this and you're trying to attach both of these. So there's going to be a lot of like proton transfers and stuff like that to get you to your product, which is going to look like this, right? This is what my students like to call a little house. But the thing I want to emphasize is that in order to protect, you have to attack the thing. So the one that's more reactive is the one that gets protected, which makes sense because that's what we're trying to do. So we protect the aldehyde. And now let's go ahead and use a reducing agent. So we can use like NaBH4. And we'll get our OH there. And we're still protected. And ultimately, when we want to deprotect, we'll use H plus H2O. So a couple of things I want to mention. First of all, this is generally what you see. It's 2 carbons, but you can technically do 3 carbons. The reason for this is, do you see how 2 carbons led to a 5-membered ring? If you use 3 carbons, it would be 6 members, which is perfectly fine. Just don't do more than 3 and don't do any less than 2. That's one thing I want to mention. Second thing I want to mention is acetals and ketals and all that stuff. So this right here is called an acetal, but we'll talk about like what that means. So if you have a protected group that came from an aldehyde, it would be an acetal. If it was protected, it was protecting a ketone, it would be called a ketal. But this is not the best way to look at it. Technically, what an acetal and ketal is if you're bonded to 2 OR groups, okay? So if you came from a ketone and you're bonded to 2 OR groups, this would be called a ketal. If you came from an aldehyde and you're bonded to 2 OR groups, you would be called an acetal. But do you guys see that like when you form this sort of a structure, you're still bonded to 2 OR groups, like it's just cyclic. Like this is an OR group, this is an OR group. So this would be like a ketal. If you had this, it would be an acetal. So that's what that is. But there's also something called hemiketal and hemiacetal. So we're going to go ahead and bring this over here. A hemiketal is when one of the OR groups is actually an OH. So this would be hemi, and it's ketal because it's based off of the ketone, meaning you have 2 carbons on the side. And then the other one would be a hemiacetal because it's based off of an aldehyde, meaning it has an H and a carbon bonded to it. And if you had 2 OHs, this is just called a geminal diol. Don't worry about that. We're talking about acetals and ketals. So probably wondering, how can I make a hemi and hemiketal and hemiacetal? Basically, like anytime you make like a hemiketal, it's just going to become a ketal. And same thing for hemiacetal, right? So let's say you had a ketone here and you're reacting it with an alcohol like this. The first thing that's going to happen, like sure, you're going to attack and kick it up. You're going to get your O, right? I just shifted the proton. But you made your hemiketal. But then the thing is, you're going to have more of this present, and it's going to do the same thing. It's going to attack, kick that off, assume there's a bunch of workup, and you're going to get this. So what I just showed you right now is actually what's occurring with your protecting group. You know what I'm saying? Like when this first reacts, when you first react, you get this sort of a structure. You're going to have your OH, and you have your protecting group partially added on. But this is considered a hemiketal or hemiacetal because you have an OH and you have this OR group. But then the alcohol will come and attack again and do all that extra fun stuff, and then you get your fully protected ketal or acetal. So just keep that in mind. All right. Now, a couple more things I want to mention. We have other protecting groups we can use that will be involving the letter S, so like your thiols, as opposed to O. And they're actually better to use. I'll tell you why. Number one is, do y'all see how this acid is what deprotects? What would happen if there's a reaction in which an acid is used and you're not ready to deprotect? You can't really do anything about it. For example, let's say we have this and we want to react with the Grignard, and we have H+. Well, sure, you'll make your alcohol there, but this thing gets deprotected, and there's no telling whether this Grignard will attack this as well, right? That could be what we don't want to happen. So that could be an instance in which we don't want to use the O, and we want to use the S. So let's go ahead and talk about the S. So same thing, you can use the protecting group, but just put S instead of O. And one equivalent, that's going to protect your aldehyde as expected. Now, if we were to react with the Grignard this time, look at what happens. My aldehyde is still protected. Let's go ahead and react it with water again for fun. Nothing changes here because these are pretty stable. If you wanted to remove it, then you have to use H+, HgCl2, H2O. If you forget all this, just write HgCl2. That is what's ultimately going to deprotect and give you back your aldehyde. So that's one reason why we could use the thioacetals, right? These are called thioacetals. Anytime you see the word thio or mercapto, it just means sulfur is involved. So that's one instance in which you might want to use a thioacetal, is when we're using acidic water for other reactions. The other thing you can do is you can actually just deprotonate this hydrogen. So let's say we got this and that. For the thioacetals, you can use Bewley, super strong base, and you can turn it into a nucleophile. And you can like react with something, right? So we can use like an alkyl halide, and we can attach this whole propyl group. So then you get one, two, three. You can get that. And then, like, you know, when you're done, you can deprotect. So, like, you can use your ZN or whatever, HgCl2, and now you got a ketone. You had an aldehyde, but now you have a ketone. But unfortunately, for the regular acetals, if you use Bewley, nothing will happen. Because if there were to be a negative charge, the oxygen is not able to stabilize it, whereas the sulfur can stabilize it. So in my opinion, the S is better, but it's up to you. There's one more thing I want to mention with regards to these ketals and acetals. So we just talked about how to go from a ketone to a ketal. We use the glycol and acid to make this. We also talked about how to reverse this. How do we go backwards? You just use acidic water. But what exactly is happening in this reverse step? You are essentially protonating both of these oxygens and removing them. And this central carbon right here gets double bonded to an O. So on the top, we reform our glycol that floats away. And on the bottom, we get the carbonyl. This O comes from the water that's being involved with this reaction. So if they gave you, once again, if they gave you a reaction on your reaction page that looks like this, you know what to do, right? You're just removing and adding a carbonyl. You had this and this. But don't forget what is really happening. You're protonating and removing. That's important to know because what if it presents differently? Let's say they gave you this and you're reacting with acidic water. Locate the acetal or ketal carbon. Obviously, it's going to be right here in blue. And this happens to be a hemi-acetal. It doesn't matter if it's hemi or if it's just like a full ketal or acetal. The same thing will apply. What is that thing that applies? You protonate and remove. Protonate and remove. So on the top, this is just going to be water that leaves. That's like a byproduct, doesn't matter. But on the bottom, when this detaches, it's still part of the overall molecule because it's an intramolecular ether. So we're going to keep that in mind when we draw our final product. So I have my first carbon here, and then I'll just continue the molecule, how it looks. Got my OH right there, and this circled carbon becomes double bonded to an O. So yeah, now it's important, right, to know what exactly is happening because it's not simply that we're forming the aldehyde. We still have this alcohol that's part of the molecule. Okay, let's do another one. They give you this, and they're like, react. You know what? I'm going to draw this. Okay, react it with acidic water. Okay, let's locate the acetal or ketal carbon right here in pink. That is going to be our ketal carbon. And so you're going to protonate the O, remove. Protonate the O, remove. If you need to number your carbons, that's perfectly fine. I'm not doing it because, I'm just drawing it how it looks. So when I draw it, you got this OH right here. You got an OH right there. Ethyl, this. And this pink carbon has like a methyl on it, so I'm going to draw a methyl right here. But this is that pink carbon, right? This is that central carbon. That central carbon becomes a carbonyl. So this would be your answer. Now, what if they gave you this and they're like, react it with acid? In this case, what else are you going to do? You're just going to protect, right? It's not this typical case of you have a glycol, but you still have these alcohols and you have this carbonyl. So what's going to happen is you're going to reform that bond on both of these, and this double bond O goes away. So your ultimate product, hopefully I'm numbering my carbons correctly, but your product would look like this. Let's do one last one. Okay, you got this plus acid. So we have our alcohols here, and we have our carbonyl right here. We have acid. So the only thing that can occur here is like a protection or just like an acetal ketal formation. So form a bond, and chop this off. And that's going to be your answer. So let's draw the product. Once again, if you need to number, you can do that. If you're cool like me, you don't need to number. So we got that on there, and then looks kind of whack, but that's what you would get. And when in doubt, you can always reverse it. So if you were to use H plus and you did the method of protonating and removing, would you get that starting material? And the answer is yes. All you got to do is just erase these bonds and put a ketone right here. You guys see what I'm talking about? So now you know how to answer these questions in case they present differently. I believe there's two more reactions or two more types of reactions to go over. So we got the Baeyer-Villiger reaction. This one is fun because you get to see MCPBA and peroxy acids, but in a different context. So if you have a carbonyl and you use your peroxy acid like MCPBA or RCO3H, okay? RCO3H is the general formula. So if you have anything like this, you're going to turn it into an ester. So you turn it like that. Essentially what happened here, you have an R1 and an R2. Your oxygen is just going to displace one of the R groups. So like in this case, it would become that. I'm going to spare you all the mechanism. But of course, when it's asymmetrical, you're probably wondering what's going to happen. So if we had this, is our answer going to be that, or is it going to be this? The answer is the top one. Because what you want to remember is that the preference is hydrogen, then tertiary, then secondary, then primary carbons when it comes to replacing. So if I had this and I'm reacting with MCPBA, well, over here I have a tertiary and over here I have a secondary carbon. Tertiary is the preferred one, so I'm going to displace that and I'm going to get this as my answer. Right? Just add an O right here. Now something else that's kind of interesting, I don't know how common this is, but if you react an aldehyde with peroxy acid, you can actually just turn it into a carboxylic acid. Now this is kind of like a stupid way to do it because you can also achieve the same thing with a strong oxidizing agent, but that is something to keep in mind, that if you were to use MCPBA or peroxy acid on an aldehyde, you actually insert the O between the H and the carbonyl carbon as opposed to the other side. So in this case, you would not make an ester. One more time. I have a tertiary side, but I have a hydrogen. Since hydrogen is the preference, you just turn it into a carboxylic acid as opposed to an ester. So that's it for the Baeyer-Villiger reaction. Let's move on to our final thing, which is very simple. It's just simply reductions. We talked about oxidation to carbonyls in the beginning. Now we're just going to talk about reduction, right? Reduction from carbonyls. So you can use LAH or NABH4. Of course, they are different, but in this case, they're not different. LAH is stronger, so it can reduce more things compared to NABH4. But if you're using something that can reduce a carbonyl, you're going to reduce it the same amount, which is going to be an alcohol. So you can make that. You can also just use H2 nickel, or you can use PD, PDC, etc. Right, platinum, and you'll still get your alcohol. What about diol? The answer is nothing. You're going to keep it as an aldehyde because diol doesn't reduce that much because it's going to be super bulky. So don't use diol, right? Use the old stuff. Use H2 nickel, LAH, etc. You can also use H2 rainy nickel, right? Whereas, like, once again, these all have different reasons to be used. Like, some things can reduce things that the others cannot. But when it comes to simple ketones and aldehydes, like, if you can reduce it, just reduce it into the same thing, which is going to be an alcohol. So these are all options to make into an alcohol. But you can also reduce carbonyls in the sense that you can just completely remove it. And this is something from last exam. Remember, you can do Clemmensen reduction, and that would give you just a simple propane. You can also do the basic version, which is going to be Wolff-Kishner, and that will be the same thing, right? Just propane. So it depends on what you're using it for. You can use either of these. So yeah, that is it for carbonyls. It's very, very long, but now we're going to move on to amines. Just as we did with the carbonyls, we're going to talk about some non-reaction related things before getting into actual reactions. The first thing is going to be basicity. Now, I did talk about basicity in my previous exam 2 review video, but as some of y'all pointed out, I did make a mistake towards the end of it. And so if you're comparing what I'm saying now to what I said then, just ignore what I said then and listen to what I'm saying now, because I have the officially verified correct information. As far as the mistake I made, I'm gonna leave a comment or something in the comment section to address it. But don't worry, whatever I'm telling you right now is correct. So to begin, what is a base? In this context, we're gonna talk about nitrogens or amines. So amines, they have lone pairs, and lone pairs are going to be used to bond to things. So we'll just use like a simple H+. The lone pair forms a bond with the H, and you can get a bond formed, right? So like that. The reason I'm bringing this up is because if your lone pair is available, it will be easier to form bonds. If it's unavailable, it will be harder to form bonds, because the lone pair is what forms the bond. So it has to be available if you want to form a bond. So make sure you understand this. So obviously, if you have an amine in which there is no lone pair, then like it just can't be a base. So if you're ever like ranking this compared to other things, this would always be the worst base because it literally is not a base. So the first thing you're going to do is you look at the hybridization of the nitrogen itself. So for the nitrogen, sp3 is better than sp2 is better than sp. The reason for this is the more s character you have, the more closely your lone pair will be held to the nucleus. This is a horrible drawing, but just think about it like this. This is like an sp example, and this would be like sp3. Since the nucleus is holding the electron in, it's going to be hard to just like form a bond to something. Whereas if it's tightly held to the nucleus, it's more likely to bond to something outside. Forgive this horrible drawing. But that's like why this is the ranking. Now, this is the general rule of thumb, right? sp3 better than sp2, better than sp. It doesn't matter what's going on with the sp2 that might make you think it's really bad at being a base. It's always going to be better than sp. Okay? So let's start with let's start with like some 3 nitrogens right here. Make sure you know how to determine hybridization, otherwise you're cooked. So this nitrogen right here, right, don't forget it has a lone pair, hopefully, otherwise it can't be a base. Count the electron domains, we have 4, so that's going to be S1P3, which is just sp3. But like I said S1P3 because 1 plus 3 is 4, which is 4 domains. So it's going to be sp3. All right. Then this imine right here, lone pair, has 3 domains, 1, 2, 3. That's going to be sp2. And lastly, we have our CN, which is C triple bond N, which also has a lone pair. Since it has 2 domains, it's going to be sp. So this is very simple. If we are ranking by basicity and we're saying most is rank 1, then it would be rank 1, rank 2, rank 3. So that was pretty simple because we had 3 different hybridizations. But now, what happens if you're comparing 2 things of the same hybridization? Let's talk about sp2. So draw a little imine right here, and then we'll do that. Both of these are going to be sp2. The first one we already established. The second one, it looks to be sp3. But remember, because you have resonance, and the resonance causes you to be a different hybridization, which in this case is sp2, you go with the lower one. So no matter what, you call this sp2. Okay, so we're comparing two sp2 nitrogens. So if you have both nitrogens as sp2, you're going to look at the lone pair. And sp2 lone pair is better than a p lone pair. So in this case, right, just look at what the lone pair can do. Over here, the lone pair can't do anything. Like, it can't form bonds or nothing like that. It's stuck on the N. So we can say that the lone pair is in the sp2 orbital. But in this case, as we just showed, since your lone pair is able to form bonds, like the pi bond specifically, and resonate, it's going to be in the p orbital, the unhybridized p orbital. And as I said, sp2 is better than p for the lone pairs. So we can say this is rank 1 and this is rank 2. Now, why is being in the p orbital bad? Because what did I say in the beginning? You need the lone pair to be available if you want to form bonds. So if the lone pair is busy doing resonance and forming pi bonds, it's not available to just bond to something like a H+. That's why that's like the ranking. All right, let's do a new scenario. Okay. As you might notice, both of these N's are going to be sp2. So the N is going to be sp2 just because of resonance and resonance. Let me draw an extra bond. So both N's are sp2 and both have resonance. So both lone pairs are in the p orbital. So now what do we do? If both sp2n have Lp in p orbital, you're going to look at quality of resonance, i.e. aromatics. So in this left molecule's case, do y'all see how the benzene is a benzene? It's aromatic as is. If the nitrogen were to do resonance with it, you're disrupting the aromaticity of it. Whereas in this case, there's no disruption of aromaticity because there's no aromatics, right? In fact, this resonance is actually pretty good because you get to put the negative on the O. Obviously, it's still not like the best because it's better to just have no charges, but there's nothing wrong with this resonance structure. But there's a lot of wrong things with this. If something's aromatic, it's really difficult to ruin the aromaticity because aromatic things like to stay aromatic. Therefore, this resonance that we did is very unlikely to occur. It's still possible, okay? This is still a benzylic nitrogen, and it's still sp2, still has resonance, but it's horrible resonance because it's going to affect the aromaticity. So that tells you that this lone pair is more available to bond to other things because it's not busy doing resonance as much as this one is doing. So if we were to rank both of these by basicity, the right side would be rank, oh my God, I'm stupid. The left side would be rank 1 and the right side would be rank 2. All right. Similarly, let's do this example. And we'll compare it to that. Both of these are sp2 nitrogens. Both the lone pairs are going to be P. In the left molecule's case, the lone pair is contributing to aromatics, right? The lone pair is what allows this to be an aromatic compound, right? Because you have 2, 4, 6. It's cyclic, etc. Right? We're not gonna get into the details, but this is an aromatic compound. If you were to take this lone pair and bond it to something and form a structure like this, the molecule is no longer aromatic. And as I told you, it's very difficult to break the aromaticity of something. This lone pair is super unavailable as a result. What about over here? You got some resonance, of course. But is it aromatic resonance? The answer is no. Which means that this is going to be more available compared to the freaking aromatic one. So if you were to rank this by basicity, this is rank 1 and this is rank 2. So that's what I mean by look at the quality of resonance and look at aromatics. If your lone pair contributes to aromaticity, it's going to be very, very low in basicity. If your lone pair resonating breaks aromaticity of something else, then it will be more basic than something else. Okay? But no matter what, guys, all that stuff we talked about, they're still going to be more basic than SP. That's just how it works. All right. Let's say we're comparing these two by basicity. Erase that. Okay. Well, both of these are going to be sp3, which means they're lone pairs on sp3 because it doesn't make sense for it to be anywhere else. So now what you can do, right? I'm going to write like number 4. If everything is the same, look at induction or inductive effects on resulting positive charge. So let's go ahead and treat these both as a base. Both of these will accept a proton. What happens? Positive and positive. The only difference between these two molecules is that the right side molecule has some extra electron donating groups compared to the left side. And electron donating groups are good for positive charges because you're stabilizing them, right? You're stabilizing by introducing some negative density to something that's lacking it. So that's going to stabilize it, which means that the right side is more basic because the conjugate of it ends up being more stable. So the ranking would be like that. So keep all these in mind and you'll be good. All right, before we get into reactions, one last thing I want to talk about is that nitrogens cannot be chiral. Well, they can, but it's hard to determine. So you could have an N with 3 different substituents on it, and you have a lone pair. But the thing is, the N does this thing called a lone pair inversion. And so the lone pair will literally just go down here. And when you do that, it like changes up everything. And it can just freely rotate between each other. And so even if one of these is S and one of these R, you can't say that it's always S and always R because it can just become either or. This is not important for this class. I'm only bringing this up because it could show up on your MCAT. It showed up on mine and I was like, what the hell? So just know that N's are not considered chiral because they can become either enantiomer. Now we're going to go ahead and begin with the actual reactions. First, we're going to talk about synthesis of amines because you have to be able to synthesize them if you want to react them. So start with the carbonyl and react with a primary amine. If you remember from the last chapter, this is going to give you an imine. Now the imine, if you react it with LAH, can just turn in to that. It can turn into your secondary amine. Another thing you can do, let's say you want to make like a primary amine. I'll tell you right now, this reaction right here with NH3, technically you could get this and then say LAH turns it into a primary amine. But from what I heard, this is very unlikely to happen because of unwanted side reactions. So if you want to make a primary amine, there's something else you can do. Reacting with NH2OH and acid. This is going to give you what's called an ox-ime. It's just an ox, like oxygen, and then ime, like amine. Nobody cares, I guess. So you're going to make this, and then you can use LAH, and that will give you a primary amine. That's like the preferred method of making your primary amine. If you're wondering how do we know this makes an amine, I told you that a primary amine leads to an amine. This is technically not primary in the sense that you're not bonded to a carbon, but the way I look at it is you're bonded to one non-hydrogen substituent. And remember, the hydrogens all like float away, but the non-hydrogen substituents stay on. So like in this case, you just start by attaching the N with the non-hydrogen substituent. If it can afford another bond, then you form a double bond. If it can't, then you don't. But in this case, you can, right? So you form an amine. So that's how you can remember to make this. But this is the preferred method of making a primary amine. All right? This is going to be a very whack reaction, but let's say you're using a secondary amine. I told you that technically it leads to an enamine, but I also showed you that prior to this, you start with an iminium, which is an imine with a plus. And then, I told you like, oh, after tautomerism, you become this thing. But if you don't let the tautomerism happen, and instead you react this guy with Na, CH3CO2, 3BH, you can actually convert this into that tertiary amine. Probably unlikely to see this. If they do show you, they're going to give you some description about it, but it's still like a reaction. So we just talked about how to make primary, secondary, and tertiary amines via like the reductions and stuff. Let's talk about some more stuff. We'll go with an alkyl halide. You can react it with Na3 and get this, right? It's just SN2. Now, when you have an N3, you can also reduce this. And what is it going to become? NH2. So I know we have 3 nitrogens here, but 2 of the nitrogens will float away. So like the way you can approach this is just cross out the 3 and put an H2. That's like the simple way to approach it. That's what's happening here. So yeah, if you have an azide, you can turn it into that amine. What about cyanide? So we'll do NaCN. Same deal, you're going to do SN2 and get a CN. If you use LAH, you also turn it into an amine. But as I've mentioned in the past, please keep track of your carbons. The C is indeed a carbon. So you have 4 carbons present. So you're going to make an amine with 4 carbons. So 1, 2, 3, 4. And then you have your NH2. That wasn't the case for the previous one because there's only 3 carbons. But in this one, the C of the CN is a carbon. So make sure you account for that in your answer. What else can we do? If you remember from the last exam, you can turn NO2s into NH2s. So the main method was to do Clementon reduction. So you could turn it like that. But another thing you can do is simply H2PD or whatever, some sort of catalyst, and you can turn it into NH2. By the way, guys, if you had a carbonyl and you use H2PT, you're not going to reduce the carbonyl. If you use rainy nickel, then yeah, it's going to reduce it. But if you use something like this, it will selectively reduce the NO2. So that's something cool to keep in mind. So we have all these methods to form amines. And obviously, you can do the typical reacting via SN2. So like you would just get this, but that's like stupid because we already have an amine made. So we're talking about how to make an amine from a non-amine in those previous ones. Okay, now we're going to talk a little bit about some aromatic things like EAS and NAS. So EAS and NAS are things from the previous exam, but we're going to switch it up to a pyridine, which is going to be a benzene with a nitrogen inside of it. So something like that. If I were to give you this and I said, do a Friedel-Crafts alkylation on it, where would it go? Well, when we had a benzene, it didn't matter because they're all the exact same carbons. So you can place it anywhere you want and it would be correct. But now we have an N present, so we can't say that our carbons are all identical. What I want you to keep in mind is that the N will act as an electron withdrawing group or like a deactivator. With that in mind, if you are to add something via EAS, it has to go meta to the N. So you're going to place it either here or here. This is ortho, this is meta, and this is para. Right? So any of these circled positions are going to be where you place it. So in this case, we can do that as our answer. That's all I'm going to say for EAS. If we talk about NAS reactions, and we have our pyridine, and let's say we have like a leaving group here, and we want to react with NaOCH3. Remember that for a substitution reaction to occur on an aromatic ring, your leaving group has to be either ortho or para to a electron withdrawing group. So as you can see, our leaving group and our electron withdrawing group are para to each other. So we can do a typical NAS substitution. So in this case, it works. And so your answer would be that. All right. Now we can talk a little bit about alkylation of amines. So if you were to have an amine like this, don't forget this is a whole nucleophile and it's a strong nucleophile. If you bring in methyl iodide, it can react with it, right? Attack the carbon and kick off the leaving group, and you'll end up with this. Obviously, it's going to be positive, but like through a workup step, it becomes just NH. But then the problem is it can occur again. So there can be more of this present, and it will attack, kick it off, and then you basically turned it all the way into a tertiary, which can react again. This is called exhaustive methylation or alkylation. So you can get this. The way to prevent this is just simply using an excess of your amine. So if you have an excess of this and you're reacting with like one equivalent of your alkyl halide, it's only going to do it once. You know what I'm saying? So it's not an issue. I'm just mentioning this. So that's alkylation, just typical SN2 with your amine. We can also do acylation. Acylation refers to making like carbonyl groups. So if we have an amine and we react it with an acid chloride or I guess technically carboxylic acid works too. But if you have this, you're going to essentially replace the Cl with this whole group. So your answer would be that. And we're going to talk more about this stuff like in the carboxylic acid and derivatives chapter, but your nitrogen is going to attack this electrophilic carbon to kick up that pi bond. And when you do that, you're going to have an O minus, you're going to have your Cl, and you have your N that you just attached. And this will kick off a leaving group, right? So we're going to kick off the chlorine to reform the pi bond. And so you end up with that. That's like how that works. So this is like the acylation reaction, but it actually has a very important purpose. It can serve as a protecting group. I'll tell you a very important instance of when this occurs. All right, let's say we have a benzene and it has an NH2 on it. This is called an aniline. So let's say we have a benzene with NH2 and we want to add a nitro group. To do it, you have HNO3, H2SO4. So most people would think, okay, I have an NH2, it's an activating group, so my NO2 would just be placed ortho or para. So you get this. But it turns out this is technically not the correct answer, because look what happened here. We have a amine right here. And okay, it's not the most basic because it's sp2, but it's still decently basic. We have a base and we have these strong acids present. And so what ends up happening is before the reaction occurs, your amine gets protonated into NH3 plus. And then the reaction occurs. Now, why is that an issue? Because when you form NH3 plus, this is now going to be an electron withdrawing group, which is meta-directing. So then, when you add your NO2, it's actually going to be over here. It's not going to be ortho or para. So in order to prevent this from occurring, we can protect it via an acylation. So if we had our NH2 and we react it with an acid chloride, you can turn it into an amide. And this amide is significantly less basic because the lone pair is busy resonating with the carbonyl. Okay, so now when we do HNO3, H2SO4, my amine is still going to be an activating electron donating group, which means that my NO2 will be placed para to it. And after this, right, obviously I have to ultimately deprotect. And so it's very simple. If you know your carboxylic acid reactions, you can just hydrolyze it. So H3O plus, and that will give you your amine again. You have your NO2 right there. So that's something you can do. That's where acylation can be helpful. All right. Very quickly, we'll talk about tosylation. So you can have NH2 and react it with tosyl chloride and just turn it into NTS. There's not much else I have to say about this. Other than that, you can do it. Like tosyl is this. And so the N can just attack and kick off the chlorine and turn into what's called a sulfonamide. So you can have your N bonded to an S. That's really it, to be honest, though. Just wanted to throw that out there. And and technically that can serve as a protecting group. But the thing is, it's really hard to deprotect it, so I don't know. Next, we're going to move on to the Hofmann elimination with regards to amines. So we'll go ahead and use this example. All right, the first step is going to be using like an alkyl or usually like a methyl halide. The N has a lone pair and it's able to do nucleophilic attack. So it's going to attack, right? It's going to attack the carbon and kick off the iodine. When you do this, you make an amine salt. Or, just in other words, sorry guys, I'm going to stop using advanced terms. I'll just speak in simple manners. You make an N plus, which is a good leaving group because when it leaves, it will be neutral. And so now we're going to do an elimination, okay? The second step is going to be Ag2O, H2O. And as a lot of y'all know, it does elimination. But why does this work? First of all, when you kicked off this iodine, the iodine's floating around as a negative. That's why I called it a salt, because you have an iodine and an N plus doing salt type interactions with each other ionically. So now you introduce Ag2O. What is Ag2O? Ag2O, you have two of these Ag pluses, and you have an O2 minus. One of the Ag pluses is going to steal the iodine and form a precipitate essentially with AgI. Something like that. I might have just made that up. And now you have AgO present. And you also have H2O. The O is going to take a proton, and now you're going to have Ag with OH, and you also have an OH over here. That might have been confusing as hell. I only included this for the tryhards, but for everyone else, don't worry about it. Ultimately, what I'm trying to say is that you have an OH present. You're going to have a hydroxide present. So you got this, and you have that. Now, this is going to do an elimination, in E2 specifically, but it's going to do Hofmann elimination. It's going to take the proton from over here, form the double bond, and kick off your leaving group, and ultimately, you get this as your answer, and your N left as a trimethylamine. But why does this occur? In the past, we were taught that if you have an E2 reaction and you're using a bulky base like tert butoxide, it does Hofmann because the base is bulky. But over here, a hydroxide is not bulky. The thing that is bulky is your leaving group, right? If you guys remember, when you're doing E2, you have to have anti-coplanarity between your leaving group and the hydrogen that you want to remove. If you try to make this anti-coplanar, it's going to be very, very sterically hindered. I mean, to begin with, the molecule is sterically hindered. So because of that, no matter how big or small your base is, it's going to take the more easily accessible proton because it's easier to make this anti-coplanar to the N compared to the other side. So it takes it, kicks off the N, and you end up with your Hofmann elimination product. So that's what happens. There's another type of this reaction. It's called the Cope reaction. It's very similar. So we're going to have our N, and we're going to react it with H2O2. So H2O2 is a peroxide, and peroxides are notoriously weak in their O to O single bonds. They're very weak because they both have an oxidation state of -1 as opposed to their typical -2. So with that in mind, the nitrogen is going to bond to one of the O's and kick off the other one. When you do this, instead of methylating, you just added an OH, and you're still positively charged here. And what happened to the other OH? Well, it's a hydroxide ion. And for the same reason as previously, it's going to extract the more easily accessible proton, do some bond shifting, and lead to a Hofmann elimination product. And your nitrogen byproduct is going to be that. I definitely recommend knowing that you form this type of a structure because they might ask you to draw both products, or they might ask you something with regards to mass spec or something like that. I saw it on a previous year's quiz, so it could show up on the exam, who knows. But product-wise, for the carbon, you just make like a Hofmann product. Okay, let's move on. I'm going to talk about diazoniums, diazonium salts. This is especially helpful for your benzene reactions. We have an NH2 and we can do a lot of things with it. But the first thing you have to do is convert it into a diazonium salt. So the reagent here is NaNO2 HCl. That's going to turn it into an N triple bond N. And you have like a plus right here. And sometimes you'll see like a Cl present, right? Like sometimes people write this out like N2Cl. All the Cl is doing is acting as like a counter ion, but you're really looking at this thing. And so since your N is positive, it's actually a very good leaving group. It's such a good leaving group that if you wanted to do a reaction, like a nucleophilic reaction, you don't need to have an electron withdrawing group para or ortho to it. That's just not necessary for this. Now, obviously, you can't do like literally anything you want, but you can do a lot of things. So the first type of reaction we can do is to turn it into an alcohol. So if you use H2SO4 or some strong acid like that, you know what, let me turn it green. Okay. You're replacing the diazonium with an OH. If you use HbF4, you can replace it with the fluorine. And my favorite one, if you use H3PO2, it's gone. Now, obviously, you replaced it with a hydrogen, but like we don't draw hydrogen, so it's kind of like you just removed it. This is very helpful because this is like one instance in which you can just completely get rid of a benzene substituent. So definitely know this. Now, some other reactions we can do. Let me draw this again. We can do what's called the Sand-Meyer reactions. So Sand-Meyer usually involves a copper 1 ion, or like a Cu plus, and you just attach things to it, right? So what does that mean? If you did CuCl, you're saying that the Cl is going to attack and replace, so you get a chlorine in place of it. If you use CuBr, you're going to replace it with a bromine. If you use copper iodide, you're going to replace it with an iodine. Now remember, if you want to add fluorine, you have to use HbF4. You can't do CuF. It's not going to work how you intended to do. So if you need to do fluorine, use HbF4. But for the other three halogens, you can use the Sand-Meyer reagent. All right. Lastly, for this chapter, we're going to talk about the Hofmann rearrangement. Guys, forgive my handwriting. My hands are hurting really bad right now. Essentially, what happens is you're going to have an amide, and you react it with Br2 and NaOH. Without getting into mechanisms and details like that, your answer is going to look like this, RNH2. So essentially what happened is you completely got rid of this group and connected these two together. And it's supposed to leave as CO2, by the way. So let me give you some examples on this. It's kind of tricky at first, but once you get the hang of it, it'll be much easier. So let's count, I guess, like our carbons here. We got 1, 2, and then we'll say the N is 3. You're going to completely get rid of carbon 2 with the O, and you're going to bond carbon 1 and 3 to each other. So chop this off, and that will be your answer. So you got your carbon 1 right here, and you're bonding it to atom 3, which is an N. So you got this. If I have this and I'm reacting, it's supposed to be a cyclohexane, by the way. All you got to do is draw your cyclohexane, chop this off, bring the N over there, and you're going to be bonded to the NH2. That is it for amine reactions. Moving on to carboxylic acids. Guys, this should not take more than 10 minutes. If it does, just kill me, because there's no way. This chapter is so short. So with carboxylic acids, if we want to synthesize them, we have many methods. Most of these we know, a couple newer ones. So we'll talk about the ones that we are all familiar with, hopefully. If you have a primary alcohol, you have to use a strong oxidizing agent, such as KMNO4, chromate, dichromate, etc. And you can turn this into a carboxylic acid. Make sure not to use anything like the acronym ones like PCC or SWERN, because these are just going to give you an aldehyde maximum. And also keep in mind that in order to make the carboxylic acid, you have to have a primary alcohol, because if you have a secondary or a tertiary, there's not enough space to make 3 bonds to O. For example, a secondary, no matter what you use, strong or mild, it only makes a ketone. And tertiaries cannot even make anything. So that's one method. What about alkenes? We can talk about alkenes now. If you have an alkene and your sp2 carbons have hydrogens present, as you can see over here, right? We have an H and an H. I'm just going to erase them because we know there's H's there. But if you have a situation like this and you use KMNO4 hot concentrated, it's going to make carboxylic acids. So you split it, you separate, and when you draw them, you do the usual of sticking some O's on the double bond. And if you have space present for another bond, which in other words means you have hydrogen present, you turn it into an OH. Because we're oxidizing, right? We initially had an aldehyde, and aldehydes become oxidized into carboxylic acids. So you're going to get carboxylic acid here. What if I had this, and I'm reacting with KMNO4, split it, separate. One of them is going to be a ketone. The other one is going to be a carboxylic acid, because only one side had a hydrogen present. Now, make sure you don't use ozone. Do not use O3 with DMS or zinc, because this is mild, so it's only going to give you aldehydes. Now, technically, you can actually use ozone to make carboxylic acids if you were to use an oxidizing agent like hydrogen peroxide. This would actually give you carboxylic acids, but I don't believe you'll have to know this. It's more of an off-semester thing. But I'm just telling you in case somebody's out there saying that I'm wrong. No, I know you can make carboxyls out of ozone, but as far as y'all need to know, at this school, ozonolysis cannot do it because DMS and zinc are reductive, so it only makes aldehydes maximum. So if you want to make carboxylic acid, use KMNO4, hot concentrated. Now, what if we talk about alkynes? Over here, it doesn't matter. You can use KMNO4 or you can use O3. Both of these will give you carboxylic acids because we're dealing with a triple bond. So you split it and separate. Count your carbons. Both sides have 2. So you got 1, 2, and you got 1, 2, and then just complete it into a carboxylic acid. So you got this, and you got that. If I had this, split it, separate. One side has 4 carbons, so 1, 2, 3, 4, turn into carboxylic acid. The other side only has 2 carbons, so you're gonna have a 2-carbon carboxylic acid. Now, by the way, anytime you have like a terminal thing, so let's say you had that and you reacted with KMNO4, technically the right side, it's going to become this. And whenever you have something like this, like a formic acid, and you're oxidizing it, it's just going to readily become CO2. Same thing would happen for if you had a terminal alkyne. Don't worry about it too much because this was more of like an OChem1 thing, but that's something to keep in mind. Cool. Now, we're going to talk about some of the newer things. One is going to be with the Grignard. So normally when we have Grignards, we just see alcohols being formed. Like if I had a Grignard and I reacted with the ketone, you attack the ketone, becomes an alcohol eventually. But if you use CO2, what's going to happen? Well, I'm telling you right now, it's going to become a carboxylic acid. But how does it work? Draw out your CO2 like this. At this point, we know really well that this carbon is going to be electrophilic. And so your Grignard will attack this carbon and kick off one of the pi bonds onto one of the O's. And so when you do that, you have a double bond O, your C. Now you have an O negative, and the other side, we have our Grignard. There's no group to kick off, right? These two O's are resonating with each other, so it doesn't matter if you reform the pi bond, you're just bringing it to the other side. There's no group to kick off, so ultimately, after a protonation step or a workup, you get your carboxylic acid. But what I want to mention is that whenever you do this reaction, just remember that you're adding a whole extra carbon. So you're starting with a 2-carbon molecule and you ending up with 3 because you're doing a carbon-carbon bond reaction. So you're reacting with CO2, okay? Finally, we have our nitriles. So let's say we have this. If you react with either H3O plus or even negative OH, right? Acid catalyzed or base catalyzed hydrolysis, this will also give you a carboxylic acid. And so you're going to have 2 carbons because you're starting with 2 carbons and you get this carboxylic acid. Now we're going to talk about how this nitrile one works because it's one of those mechanisms that could show up. And it might seem annoying and scary and chaotic, but you have to just keep in mind, okay? You have to keep in mind that you're trying to remove this N and you're trying to add these 2 oxygens. That should help you when you're working out this mechanism. I'm telling you right now, I don't even know the mechanism off the top of my head, but because I keep what I just said in mind, I'm able to logic everything out. What does that mean? Keep doing things to make this N a leaving group and keep doing things to keep the O's on and not leaving groups. I'll show you what that means. So the first thing that happens, you have an acid present, and anytime you have something with a lone pair and you have protons present, you're going to protonate it. So we're going to start off with this. And protonation is good just because you're making this more likely to break a bond, right? The N wants to take one of these pi bonds because it's positively charged. And so you're setting that up by protonating it. Now we're going to have a water molecule pull up and it's going to attack this electrophilic carbon and break off one of the pi bonds. So now when you do this, you're going to have a double bond NH and you have your OH2 plus. So this is what I mean, right? We're trying to keep this O attached, but right now it looks like a leaving group. And we're trying to remove the N, but right now it looks like it's chilling there, like it's not going to leave. So we want to do things to make the N a leaving group and to make the O stay. So in this case, you're going to do a proton shift. Proton shift means we're going to remove one of these H's from here and transfer it over there via a water molecule helping us out. So you're going to have your N. Now it's NH2 and it's positively charged. And the OH2 is now just an OH. Okay? So the N has another bond to break, and how does it break its bond? The O is going to form its own pi bond and kick this up like that. Now I'm going to redraw this. I'm going to put the O up here. So we got OH, we have our NH2. Okay. Now, you could say that the H moves over here, but technically what happens is another water molecule will come in, and it's going to attack this and kick that up. So now OH, and then we have our NH2, and we have our water molecule. Same deal, we're trying to get rid of the N, and we're trying to keep the O. So do another proton shift, and we're going to keep the OH here, have another OH there, and we have the NH3+. So what do we do now? Form a pi bond with one of these oxygens. It can be either or. Form this pi bond and kick this NH3 off completely. Now you have an OH plus, and then you have your OH right here. And then we're pretty much done, right? All you got to do is a workup step. So you can just write minus H plus. Like it just leaves because of a workup. A base will come in and take it, and you end up with your carboxylic acid. So I know it looks kind of messy, but all I did was I just moved protons around, and I kept trying to form more and more bonds with the O's, which is what I'm trying to end up with. And I'm trying to break as many bonds as I can with the N, because I ultimately kick it off. So that's what I did. And this was the acid catalyzed. The base catalyzed is similar, but you just don't have the protons present. I'm not going to go over it. If you're curious, you can look up a mechanism, or you can even attempt it on your own, but it's going to be very similar. Moving on, we're going to talk about reductions of carboxylic acids. So remember, carboxylic acids, you need something strong enough to reduce it. You cannot use NaBH4 because NaBH4 is not strong enough. NaBH4 can only reduce ketones, aldehydes, and acid chlorides. So what we can use, though, is a typical LAH. So LAH will turn it into a primary alcohol. If you have a carboxylic acid and you use the bulky version of LAH, like diol, this will also reduce it, but into an aldehyde. Let's talk about selective reduction. So if you were to react this molecule with NaBH4, what's going to happen? It's not strong enough to reduce the carboxylic acid, but it can reduce the ketone. What if you used LAH? What's going to happen? It's strong enough to reduce the carboxylic acid, but it also means it can reduce the ketone. So what if I want to make it such that the carboxylic acid gets reduced, but not the ketone? Well, there's two ways to go about this. One is to protect your ketone, using the whole protecting group and so on. That's a perfectly valid option, but you can also do this in one single step using BH3-THF. BH3-THF, for whatever reason, is very selective for carboxylic acids. So if you have both a ketone and a carboxylic acid in, and you put BH3-THF, it's going to reduce the carboxylic acid so fast. The ketone will eventually get reduced, but I'm talking like the difference is between minutes and hours. The carboxylic acid will get reduced so fast that you don't have to specify like one equivalent. You can just say BH3-THF and say this is your answer. If you just had a ketone and you reacted with BH3-THF, yeah, sure, you can say it gets reduced, although it's not the best option to use. But if you have both the carboxyl and a carbonyl, just reduce the carboxyl. Perfectly acceptable. So this is a one-step selective reduction of carboxylic acids. Next, we're going to talk about how to go from carboxylic acid into ketones. So all you got to do is react it with an organolithium. In this case, it will be CH3Li because we're attaching one right there, and so that works. If I want to make this where I have 3 carbons, 1, 2, 3, bond to Li. And remember, for the 100th time, do not use Grignards or even CuLi. It has to just be the Li, the organolithium. And now we can move on to our carboxylic acid derivatives. I'm going to go ahead and start off by writing out all of our carboxylic acid derivatives because it's important to know the order of reactivity and exactly like what can turn into what. So we have acid chlorides or acid halides. We have anhydrides, thioesters, esters, and then amides. And technically, carboxylates. Now, to a lot of y'all's surprise, a nitrile is also considered a carboxylic acid derivative, but we're going to exclude this from the ranking because they don't generally ask you to rank this amongst other things. But the reason it's a carboxylic acid derivative is because you can just turn it into a carboxylic acid, which all of these can do. So this is the ranking of reactivity, and it's going upwards, right? So the carboxylic acid derivative of acid chloride is the most reactive. So this is going to be increasing reactivity. And the reason for this is because all of these have leaving groups for the most part. And if the leaving group is a really good leaving group, then the molecule will react because it will allow for the leaving group to leave. The leaving group can't just leave like that. It has to be reacted with for it to leave. But if it's super reactive, then it's going to be more likely to have a reaction occur that causes the leaving group to leave. So that's why the reactivity is like this. But let's go ahead and look at the leaving groups. We have chlorine. We have a carboxylate, S minus, O minus, and NH minus. And over here, this is just like super unreactive. Like I just included it for the vibes, but like it's not reactive at all in the sense that you can't attack this carbon. If anything, this would attack something else, but you can't attack the carbon because there's no leaving group. Okay, so we're just gonna scrap this. I think we kind of understand why it's the least reactive in terms of being an electrophile. So why is the leaving group stability like this? There's 2 ways to go about it. The weaker the base, the better the leaving group is. So when we have our periodic table, you can use the Bean mnemonic. So the further away you are from this B, meaning the further to the right and further down you are, the less basic you will be and the better of a leaving group you'll end up being. That's one way you can look at it. So let me ask y'all, if I'm comparing an acid chloride to an acid iodide, which one is more reactive? Well, if you look at the periodic table, Cl is above I, and we want to be below, right? We want to be further to the right and further down. So since iodine is on the same level as Cl, but it's lower, it's going to be the one that has is more reactive, or it's a better leaving group. So that's one way you can look at it. The other way, which is my preferred method, is the areomnemonic. So A is for atom, R is for resonance, I is for inductive effects, and O is for orbital, but O never shows up. So when it comes to atoms, you want to be further to the right, all right? You want to look at electronegativity. I'm not going to talk about up and down right now. So take a look. We got C, N, O, F. And then let's just like add some more stuff to this. So the further you are to the right, the better off the bat. So if I'm comparing in N and I'm comparing in O, the O is automatically better than the N. Right? We're trying to talk about stability of the leaving group. So let me like draw some actual negative molecules. Let's say we have an N minus and there's resonance involved, but then I'm dealing with an O minus with no resonance. It does not matter that the N has resonance. The O is just better because the O is in a further right group on the periodic table. So that's how you look at A for atom. However, if we're comparing two things in the same group, so like O minus and S minus, now you want to look at size. So you're going to look at what's further down. So since S is further down than O, the S is actually better. But then the little caveat here is if you're comparing two elements in the same group, one of them has resonance, one does not, the one with resonance wins. So although we said S is better than O, since the O has resonance, the O is actually going to be better than the S over here. But then if I bring in an O without resonance, and I'm ranking these by stability of leaving group, this is number 1, this is number 3, this is number 2. Now, inductive effects, let's say you're comparing this to that. Which one is more stable? Well, when you have a negative charge, you want to have electron withdrawing groups and you don't want electron donating groups. So the only difference between these two molecules is that the top one has extra carbons and these are electron donating groups. Electron donating groups are bad because you're donating negative electron density to something that already has a negative charge. So that's going to be less stable, meaning that this was the better leaving group. So the way this could show up is if they're asking you which of these is more reactive, since this is a better leaving group than this one, for reasons we just established, this would be our answer for more reactive. So we kind of got the idea here. Definitely keep this stuff in mind because although I think it's very easy to remember this ranking that we have in red, they could introduce like little differences that make you think a little bit more. So in this case, let's just quickly verify. Chlorine is furthest to the right compared to any of the atoms. So chlorine automatically wins. Now we're comparing O, S, and O. We already talked about this. O with resonance is better than S without resonance. And S is generally better than O if they're identical in the sense that they don't have resonance. So that's why the ranking is like that. Then N is furthest to the left out of all our options we have. So it's going to be its own category. So it's going to be the least reactive out of these proper derivatives. And then if you already have an O negative, you can't say this is a leaving group because that would be O2 minus, which is stupid as hell. So yeah. Now, why is this reactivity important? Of course, it's important because they could ask you a ranking question. But another thing you have to keep in mind is that you can only turn into things that are lower than you. So an acid chloride can become any of these, but you cannot say that an amide can just simply become a thioester, at least not in one step, because there's like a difference in the reactivity ladder. I'll tell you why this is the case, and I'll tell you how to convert into everything. So if we have an acid chloride and we're reacting with, let's say we're trying to make like an ester. So we're going to react with an ethoxide. The first thing that happens, as always, is you attack the carbonyl carbon and you kick the bond up. Now, this is an important intermediate. It's called a tetrahedral intermediate. It's literally a tetrahedral shape. You have 4 bonds. This is important to look at because it can tell you what ends up leaving and what ends up staying. Because it's very possible that the thing that attacks is the thing that leaves, and then no reaction really occurs. So we have this. We know that the chlorine is a good leaving group, and we know that we have a pi bond that could be made. And so we form the pi bond and we kick off the chlorine, and we get our ester as intended. But now, let's say I have an amide and I'm reacting with this molecule right here. I'm going to do the typical, attack the carbonyl, kick the bond up. Now, what does my tetrahedral intermediate look like in this case? I have an O minus, I'm going to have N, and I have S. Okay, this pi bond will reform, but it has to kick off either the N or the S. Well, which one of these is a better leaving group? The S is a better leaving group. So although the S just formed a bond, when the pi bond reforms, it kicks off the S, and you end up with no change at all. Do you see this was the starting material? That's why it's important to know this ranking, because you know that you can't just readily convert to one thing or the other. It depends what is being converted into what. So for this reason, we can easily tell now that acid chlorides can become anything. We know that anhydrides can become anything below it, esters can become anything below it, and so on. But how do we go up the reactivity ladder? How can we go upwards? The good thing to know is that a carboxylic acid can turn into any of these. Let me just get rid of this stupid carboxylic. We don't need it. So the good thing to know is that carboxylic acids can become any of these. And so if we can turn into a carboxylic acid, we can turn to anything. And it's very easy to become a carboxylic acid. All you got to do is hydrolysis. So let's say we have thioester, react it with H3O plus, and you're going to make a carboxylic acid. And then the carboxylic acid, you want to make into an acid chloride, then just react it with SOCl2, and look what you did. You went from a thioester to a acid chloride. And that was not possible to do directly because the acid chloride is higher on the reactivity ladder than the thioester. But you're able to do it because you converted to carboxylic acid first. Let's do another one. Let's say we want to go from an amide into an anhydride. So let's do that. The first thing you got to do is hydrolyze. So use H3O plus. That's going to give you a carboxylic acid. And now what do? React it with the thing you're trying to attach. You're trying to attach this thing, so just make a molecule that looks like that. So you got this. And of course you can add acid if you want, and you can turn into that. So yeah, that's all I really have for this stuff. There's honestly, there's no point in going over turning into every single thing. Once again, everything else that you're trying to make is you just add the thing you're trying to make as the reagent. Like as I mentioned, if you have a carboxylic acid and you want to turn into an anhydride, use this as your reagent. If you're trying to make a thioester, use this thing as your reagent, and so on. The only one where it's different is this one, the acid chloride. You have to use SOCl2. If you want to make an acid bromide, you have to use PBr3. I'm not going to get into the mechanism of this, but just know that's the only difference. So let's do some practice. I guess keep in mind that when you have anhydrides, you're going to get like two types of carboxylic acids or derivatives. So I'll give you an example. If you have this and you react it with, let's just do this. Well, this is a leaving group, so it's going to leave, and you're going to attach the amine in place of it. So you're going to get this. But keep in mind, this leaving group that left is also a carboxylic acid now. Obviously, it's a carboxylate, but through a protonation step, it's going to become a carboxylic acid. So you get two products here. Let's do another reaction. Let's say we had, I believe I got a question like this on my MCAT. I forgot the exact details, but something like this. Anyways, we have a cyclic anhydride and we have methanol. And we know that anhydride can become an ester because it's lower on the reactivity chart. So what are we going to do here? We can choose either side as a leaving group. It doesn't really matter. We're going to say that this is the little leaving group side. So we're going to like detach it. And we're going to open this up a little bit. So we're going to have C double bond O and just number your carbons. So we got 1, 2, 3, 4, 5. So we got 1, 2, 3, 4, 5. Erase this. And the left side, right, carbon 1, is going to bond to the new thing. So we got the O with the methyl. And carbon 5 has the O that left, and it's a negative, but it becomes an OH. This would be our answer. It opens up like that. Let's talk about one more type of reaction that's a little bit different. So amides can actually be turned into nitriles. All you got to do is react with either Pockle2 or you can use P2O5. And as usual, make sure your carbons are adding up. So in this case, we have 1, 2, 3, 4 carbons. So you're going to have 4 carbons, right? 1, 2, 3, 4. And you can write this as a CN. Or you can do, I'm stupid, guys. Here, one more carbon. All right, I got 1, 2, 3, 4. Now, if you want to turn a nitrile into an amide, it's all good. Just react it with H3O+, and that's going to give you a carboxylic acid. And then you can just react it with whatever, right? If you're trying to go back to the original thing, then just react it with that, right? If you're trying to make something like this, then we'll get that as our answer. Now for nitriles, another thing to remember is that if you're reacting with the Grignard, it turns into a ketone ultimately. So you have your carbon 1, carbon 2, carbon 1, carbon 2, you're bonding to the Grignard carbon, and you have a double bond O right there. A couple more reactions I want to talk about are just like intramolecular ones. So don't forget that intramolecular reactions exist. So if you have two substrates within the same molecule, you can just react them. So if we have something like this and they say react it under acidic conditions, well, I know that a carboxylic acid plus an alcohol equals an ester. So I have both of that in the same molecule, right? The left and the right side. So I'm going to react. And so we got 1, 2, 3, 4, 5. I'm going to have a 5-membered ring. This OH will leave, and this O will take its place, right? So I'm going to have a 5-membered ring. So I'll draw that. And then it doesn't really matter. Let's put the O right there or something. By the way, guys, this is called a lactone. A lactam, if you guys have heard of this, is when you have a cyclic amide. so that's one example. What if you have two carboxylic acids together? Well, two carboxylic acids equals an anhydride. So I'm going to do that, right? So we got carbon 1, 2, 3, 4, 5. And then this is the one that attacks. That's why I numbered all the way there. But the O will attack and whatever, right? So you're going to have a 6-membered ring. So you're going to have that. And then you got your O's like that. This is the cyclic anhydride. And lastly, a little fun reaction I want to talk about is called saponification. So saponification is just the base catalyzed hydrolysis of esters. So if I had an ester and I react it with like a hydroxide, is going to make a carboxylate, which I know you guys are going to say, oh, you can protonate it into a carboxylic acid, but the whole purpose of it is to make an O-, and I'll tell you why. Normally, this reaction occurs with, goodness, I'm stupid, with your triglycerides. Or just like fats, right? And when you react this with excess of OH minus, look what happens. You're just chopping this guy off and you're turning all of these into these super long O-. Do you see how long they are? They're very, very long. What we just created is soap. That's why it's called saponification, because it refers to making soaps. And that's how soaps are made. You use fat and you just hydrolyze them and you turn them into these carboxylate salts. Now, the cool thing about this, oh, by the way, guys, if you're strictly here to learn how to do good on your exam, you can skip this, but I'm just spreading some cool knowledge. So if you care for that stuff, you can stay. Otherwise, you can skip like a minute and a half ahead. But this is soap. Now, as you might be able to tell, on this side, we have a bunch of hydrocarbons, which is non-polar. But then we have this one side right here. We have like this polar side with a negative charge. So soap has both non-polar and polar components to it. Why is non-polar important? Non-polar is important because it can bind to oils, right? Oils and fat that's on your hand. You can't just wash it off with water because water is polar. So the soap will be able to bind to it via its non-polar components. But what do we ultimately do with soap on our hands? We wash it off with water. So that's where the polar side comes in. So you can wash off with water. So tough, for real. Now you're wondering, why can't you just use this if this is considered polar? My guy, this is literal acid. I don't know if you want that on your hand. Bases are what feel soapy. I don't know if anyone has ever touched an acid and touched a base. Acids burn, bases feel like soap. That's literally what this is, a base, which is soap. So yeah, something cool for real. But I guess another thing to keep in mind, saponification, just know this name in case they tell you to rank by saponification. A common type of question they ask for ranking is they'll be like, rank these carboxylic acid derivatives by rate of blank. So they'll give you some random name, like they'll say hydrolysis, or they'll say saponification, or they'll say something like that. And if you just know that saponification is a carboxylic acid reaction, you'll know that you're just ranking by the typical reactivity of your carboxylic acid derivatives. Okay, we are done with carboxylic acid derivatives. Now we're going to move on to enolates. What is an enolate? So we know what an enol is. It's going to be an alkene plus an alcohol. Anytime you see the suffix ate or ide, it means like a anion or deprotonated version. So an enolate would just be something like that, where it's a negative enol. Now, enolates can show up in two forms. Number one is this one, or if we do a little resonance, we can get another form of it, which basically looks like a deprotonated ketone. So these are both enolates. the resonance forms of each other. And as you can see, the negative shifts between O and C. The red one is the more stable resonance form, but when this acts as a nucleophile, it's actually the carbon. So I want you to remember that these are carbon nucleophiles. The carbon is just more electrophilic than O in general, and also the energy of the HOMO is higher when the carbon attacks as opposed to the O. So that means it's going to be closer to the LUMO when it attacks with something, which means it's more likely to occur. So the carbon will attack as a nucleophile. But I do want you to remember that this is the more stable resonance form. The reason I'm bringing this up is because if you do a mechanism, you should start off in the red format. So we'll do a quick example reaction before I actually dive deeper and explain things. So like, let's say you were trying to react with an alkyl halide. You're going to start with this structure, and then you reform a pi bond, and this pi bond goes and attacks a carbon and kicks something off. And so in this case, your answer would be that, where you just attached a metal. But you started like this. That's the officially correct mechanism. But for simplicity, I'm just going to leave the negative on the carbon because I don't want to confuse anyone and make it super redundant or repetitive. But I want you to remember, in case they ask you a mechanism, if you want full points, start off like this, then form a pi bond and then attack things. But in my case, I'm just going to use this to directly attack. So how do we form an enolate? Well, you got to start with a carbonyl. So start like that. And you're going to look at the alpha hydrogens. So alpha is a point of reference with respect to something. So whenever we're talking about the carbonyls, that's like our starting point. And one position away from it will be alpha. So this will be alpha and this will be alpha. Another position away will be beta and beta. And then you can have gamma, delta, etc. We have alpha and beta. The alpha hydrogens are very acidic because, well, if you were to deprotonate, now you're able to have some resonance with the oxygen. So you want to keep your eye out for the alpha carbons. And we're going to bring in a base, like, let's say, well, you're going to use LDA because if you were to use something else like NaOCH3, NaOCH3 you can use, but it's just like sometimes this will react as a nucleophile. You know what I'm saying? NaOCH3 is both the nucleophile and the base. So if you want to prevent unwanted side reactions, they use LDA. But it's perfectly fine if you use NaOCH3 or just NaOH. But LDA, since it's very bulky, it's not going to be a nucleophile. It's only a base. And so it's going to easily deprotonate your alpha hydrogen. And either position is fine because it's symmetrical. So you form this, and now you can do different reactions where you bind to things. So the first one, for example, could be Br2. So you can attack bromine and kick this off. And you'd end up with that right there. So now I'm going to show you something cool. So let's use the same acetone, and we're going to do this reaction that shows up like this, Br2 NaOH. And so NaOH is hydroxide is a base. It's going to extract one of our alpha protons, and that's going to give us an enolate. Now this enolate is going to encounter a Br2. It's going to bond to one of them and kick off the other, and that's going to give us an alpha addition of one bromine. But we're under basic conditions, right? So we have more hydroxide present, and we have more alpha protons available, and so it's going to deprotonate this and do the exact same thing. So we're going to form an enolate again. And this is the correct position to deprotonate because you're stabilized by this electron withdrawing group. So now you encounter another Br2, and you bond to one of them and break the other one off, which gives you 2 additions of the bromine. And at this point, you can expect it's going to happen for a third time. So you deprotonate, you got your Br2, attack, kick off. So look at what we just created. This might mean nothing to you, but I'll make it mean something to you right now. You created this. Another way to write it is just CBr3. So this carbonyl, right, it was just a typical simple ketone. You have this whole electron withdrawing group right on this carbon, which makes it very more electrophilic than it was initially, right? If you're comparing these two, you have two donating groups, but now you turn one of the donating groups into an electron withdrawing group. So this carbonyl carbon is much more electrophilic, and we still have this base present. But what do we know about a lot of our bases like hydroxide? They're also nucleophilic. So this nucleophile is going to see that we have a very electrophilic carbon, and it's going to attack it and kick this pi bond up. And we're going to get this tetrahedral intermediate. And when this pi bond wants to reform, what is going to get kicked off? Will it be the CBr3 or the OH? It's going to be the CBr3. And we form a carboxylic acid, and the CBr3, take a look at this. This is considered a methyl anion, and we know that methyl is better than primary, secondary, and tertiary. Not only is it methyl, we have 3 electron withdrawing groups right on it. That makes this type of a species exceptionally stable as a leaving group. But then eventually, this is going to deprotonate the hydrogen off of the oxygen, and you're going to end up with a carboxylate. And on the right side, you're going to get your HCBr3. This is called a haloform, specifically a bromoform. I'm sure in class y'all heard about iodoform, which turns yellow in solution. But when you do this reaction, it's perfectly fine to just say your answer is a carboxylic acid because you're assuming that a workup occurred. But technically, you form a resonance stabilized carboxylate. And if you know anything about carboxylates, they're very unreactive, at least as electrophiles, which means that this reaction will not reverse. You're stuck as this. So you for sure made a carboxylic acid or a carboxylic acid deprotonated. So you're going to get this. So back to this, okay, if you're wondering, how can I stop at one single bromine? Well, the first thing you could do is just use one equivalent of the Br2. The second thing is to react this under acidic conditions. This is not a focus for this exam because I don't think they even teach you this. I'm just bringing it up in case you're wondering. So that is one thing I want to mention. So if you're doing basic, just max it out. But another thing, let's say you have this and you do the same reaction, right? Br2 NaOH. And it's excess, right? You're going to end up with 2 bromines attached. This does not count as a leaving group. You have to have 3 attached. If you don't, then nothing happens, okay? You just leave it like this, right? There's no attacking that occurs. And same with if you only had 1 attached, like this is not considered a leaving group. It has to be CX3, which means you have 3 of the halogens attached. So that is one thing I wanted to mention. And the final thing with regards to this specific reaction is if you are provided this molecule and they say react with acidic water, we know that acidic water causes our carboxylic acid derivatives to become a carboxylic acid, but this will not make a carboxylic acid. You might think it makes carboxylic acid. This just does nothing. Okay, if you want this group to leave, you have to be under basic conditions. So if you want to make that carboxylic acid, use a base, so negative OH. And we just talked about how it becomes an O-, but ultimately it can become an OH. Similarly, if you wanted to make it into an ester and you tried doing an alcohol under acidic conditions, nothing happens. So how do you turn this into an ester? Basic conditions. This is basic, right? There's no protons present. So you can absolutely turn it into an ester. Okay. And so one more thing, or one more example. If they give you this and they're like react with ethylamine, we have two potential leaving groups. We have the CF3 and we have the methoxy group. But as I mentioned 2 times already, this group, the CX3, will only leave if you're under basic conditions. If you're under acidic conditions, just don't touch it. So the answer for this would be to replace the alkoxy group. And so your product would look like this, with the CF3 still attached. Okay? Next, we're going to talk about attaching like methyls and other alkyl groups. So let's deprotonate it, make our enolate. And we can react it with an alkyl halide. So let's bring in CH3Cl. So you're going to attack, kick off, and you end up with an extended ketone. So you get that. But now the question is, what if you have an asymmetrical ketone and you want to methylate it? Will the negative charge be over here or over here? You can actually control this with different temperatures. So in one condition, you're going to have a negative on the secondary position. In another condition, you can have the negative on the tertiary position. So the way to do the top one, we're going to use our LDA, and we're going to put this under kinetic control, so negative 78 degrees Celsius, and this will be kinetic control. Over here, we're going to use LDA again, and we're going to put it in room temperature. This will be the thermodynamic control. Now you're probably wondering, if the anion is more stable at the top, why is this considered kinetic? Because secondary is better than tertiary. You're not looking at the anion, you're looking at the alkene stability. So if you do some resonance, you're going to end up with a tri-substituted alkene, which is pretty good. But in this case, if you were to do it, you're going to end up with a tetra-substituted alkene. So this is a more stable alkene, and that's very fitting of the thermodynamic nature of this reaction. This is less stable, which means that it came from the kinetic control. Then from here, you can do your reaction, right? So if you have CH3I and CH3I attack and attack, right? You end up in the first one, you're going to attach a methyl on the right side, and the second one, you're going to attach it on the left side where you already have a methyl. Now let's talk about the aldol reaction. So aldol is named aldol because an aldehyde is supposed to be involved and you end up with an alcohol, but it's not always the case. We're using aldehydes. You can use ketones. So we're going to talk about ketones. So let's say they gave you ketone and you're reacting with LDA. Well, they can like literally give you this as the question, ketone with LDA. The answer is not going to be an enolate. Like that's like stupid. That's like all you did is deprotonate. Of course, that's what happens, but that's not what they're asking for. Whenever they give you one molecule and you're reacting with something that just like deprotonates, you have to remember that this thing is in excess. So there's going to be a lot of them. So you can have like 2 of them present, and the LDA is going to deprotonate one of them, and the other one is going to be the electrophile, right? So when we deprotonate, we made a nucleophile, and when the other one is not deprotonated, it's an electrophile. So we're going to do a reaction in which we just combine the 2. So we have our nucleophile, and the carbon right here is the electrophilic carbon. So you're going to form a bond. And you always kick up the pi bond. Now what I like to do is keep the attacking molecule the exact same. So we're going to keep the ketone just like that. And we'll go ahead and number it 1, 2, 3, and we bond it to carbon 4. So we're going to form a bond to carbon 4, right? This is 1, 2, 3, and this is carbon 4. What does carbon 4 have on it? It has 2 metals, and it has an O-, which through a workup step becomes an OH. So what we just did right here is called an aldol addition. We added 2 of these carbonyls together. But this can undergo one extra step, which is dehydration via high temperatures. So you can write a triangle. And this will be leading to the loss of a water. So you have like 3 positions in which you can place your double bond. You can go here, you can go here, or it can go over here. No matter what, you're always going to place the double bond on the position that's alpha and beta to your carbonyl. It doesn't matter how many substituents end up being on the other side, you always want it to be in this position. So when you write your condensation product, it's going to look like this. And this is the answer for aldol condensation. Now, guys, sometimes your professors want the aldol addition, sometimes they want the condensation. If they put heat in the reaction, you'll know for sure it's a condensation. Sometimes they won't write heat, but like I feel like they want the condensation product. So if you want to be careful, okay, let's say they gave you this as your reaction. This is what I would do, okay? Whatever I write in pink is what I would write on my exam. I would write this product. And then I would also write, maybe like a little small, I'd write like a little heat symbol and be like that. And I'm not going to circle either of these. Let's say they wanted this answer. They're not going to get mad at me for writing this because I'm writing a completely separate step, which is not what they asked for. That's just me writing my own notes. If they wanted the dehydration product, well, I already wrote it here as the final thing. So it's a little loophole in case you're like paranoid. But of course, if they write heat, definitely write the dehydration product. Okay, what if I have a ketone plus an aldehyde and I'm saying deprotonate LDA? Technically, your aldehyde is more acidic than the ketone, but it's very possible that the ketone gets deprotonated and not the aldehyde. In other cases, the aldehyde might get deprotonated, and it's a little bit confusing. You're going to end up having both reactions. In one case, you're going to have that. In the other case, you're going to have this. And so generally, they're not going to give you something like this because even in reality, it's not going to be the best. It's not going to be the most ideal scenario. So what ends up happening, there's 2 things you can do. Number 1, you first start with the thing that you want to be the attacker. You react this with the base. You form your enolate. And once you form your enolate, then you can react it with the other thing and do your reaction. The other way around this is to just put 2 things together, but make sure that one of them does not have an alpha hydrogen that can be extracted. So if you had this, for example, this aldehyde, there's no alpha hydrogen, right? There's nothing here that's a hydrogen, and this is not an alpha hydrogen. It has to be a carbon with an H on it. So that's what you can do. So let's go ahead and complete both of these reactions. If we did the first one, we form a bond here and we kick this pi bond up. Keep your attacker the exact same. So keep my ketone and I'm going to form a bond over here. And I see there's only 2 carbons. So I'm going to draw carbon 1, carbon 2, and I have my little alcohol right there. And then if I undergo a dehydration step, double bond goes right here, so that it will be alpha beta to my carbonyl. So we're going to have this as my product. Over here, there's only one place where I can deprotonate, so I'm going to go ahead and deprotonate right here. And then I'm going to attack this carbon, kick that pi bond up. Same deal, keep your attacker the same. I'm forming a bond to this carbon. The carbon is bonded to a benzene. And it's also bonded to an O minus. And of course, there's like an H, but I'm not going to draw it in. So it's going to be an O minus, which becomes an alcohol. And in this case, I only have one place where I can even draw the double bond. So I'm going to do that, but it doesn't matter. I'm always going to draw alpha beta to my carbonyl. So this type of a structure that I keep talking about, this alpha beta unsaturated carbonyl, there is another name for it. You might have heard of MVK, or methyl vinyl ketone. Technically, MVK is when you're like, this is specifically what an MVK is, where it's literally like a methyl vinyl ketone. If you have any more carbons than this, then it's not really an MVK. But if you ever heard of MVK, you can, like, for now, just use it interchangeably with alpha beta unsaturated carbonyl. We're just focusing on the fact there's a double bond right next to it, or conjugated. I'm probably going to refer to them as alpha beta unsaturated carbonyl, but if I say MVK, I'm referring to the same thing. So it's cool that we know what this is, because now we can do our next reaction, which is the Michael reaction. So a Michael reaction is going to be an alpha beta unsaturated carbonyl plus an enolate, and you're going to react them. Now, if you look at this alpha beta unsaturated carbonyl, yes, we have a carbonyl that's going to be electrophilic, but there's also another part of this molecule that's electrophilic, and that is going to be the beta carbon right here. So we have two options. We have the orange and we have the beige arrow. Which one is our enolate going to attack? In the event that you have both of these options, you have to see what type of a nucleophile you have. If you have a resonance stabilized nucleophile, it's going to go for this beige position. So we're going to say resonance stabilized or weak nucleophiles. And if you have an unstable or just super strong nucleophile, then you go for the orange position. It just has to deal with differences in affinity. So when I say resonance stabilized, I mean, take a look at this. It's an enolate to resonance stabilized. So this is actually going to go for the beige position. But if I had something like a CN minus, it would go for the orange position. Another example of something that would attack here that's labeled as weak would be your organocuprates. Remember, organocuprates are not like the best. So this would end up attacking on the beige position as opposed to the orange. Now, if you're wondering why is it the beta carbon, not the alpha, take a look at the resonance structure. Let's go ahead and bring this down, kick that up. Do you see how the beta carbon has a plus on it? That means that when there's a double bond, there's a partial positive on it, which means it's electrophilic. So that's why it's going to be that position. Now, if you attack this carbon, you're going to do what's called a 1,2 addition. So you get like this, like an OH, and then we'll put like a nucleophile right here. It's literally like you're bonded over here. This is 1, this is 2. That's how the 1,2 works. If you bond to this carbon, well, it's going to be 1, 2, 3, 4. That's called a 1,4 addition. So that's like another way you can remember the beta carbon, because I feel like people remember 1,4 a lot. So yeah. Anyways, let's do this actual reaction now that we established where we're going to attack. So we're going to draw an arrow right here, and this pi bond has to move. So it's going to move over here and kick this up. So the way I like to draw this, I draw the attacking molecule on top, and then I form a bond going downwards, and then I attach the thing that I just attacked. So I'm gonna draw it like a little long right here. And we're gonna go ahead and number this. Carbon 1, 2, 3, 4, 5. So we bonded to carbon 4, and then just finish it off, right? Carbon 4 is bonded to carbon 5, and it's bonded to carbon 3, 2, and 1. And between carbon 2 and 3, I have a double bond, and carbon 2 has the O minus on it. Now, eventually what happens is that this comes back down, and this bonds to a floating proton. And your ultimate product is going to be that. So here's a little shortcut. Do you see this right here? This is our starting material, the ketone. And you see this right here, this is our alpha, beta, unsaturated carbonyl. The only difference is that my double bond is gone. But other than that, I just formed a bond between the two. It's literally like you just form a bond here and you break this off. So that's like a little shortcut. So let's draw this again. Now, in order for this to have occurred, right, how did we make this enolate? Well, we had to have started with the ketone and then we used like LDA or something like that. So we still have base present. We still have base present over here, and it's going to start deprotonating things. It's going to start deprotonating all the alpha positions. So we're going to get this one, maybe. What do we get if we deprotonate that? We'll get this. Okay, now what is the significance of this? You're going to see if we can do an intramolecular aldol. So if this were to attack this carbon, what would end up happening? Take a look at the number of members in the ring that you would have. This is 1, 2, 3, 4. So if this were to attack, you get a 4-membered ring. That's not good. So it's not going to get deprotonated. Or it might get deprotonated, but then reprotonated. What about this one? You deprotonated. If you were to attack this carbon, well, it's 1, 2, 3, 4. 4 members in the ring. That's still like pretty bad. You want to have 5 or 6 members. So eventually, this side will get deprotonated. And if it were to attack this carbon, how many members are in the ring? 1, 2, 3, 4, 5, and 6. Since you can form a 6-membered ring, you're going to pursue this. Now, I have to mention something really, really quick. You might be wondering, like, can we deprotonate this one and attack this carbon? Because it's also going to form a 6-membered ring, right? 1, 2, 3, 4, 5, 6. Honestly, guys, I have no clue what's going on anymore. This seems very logical, but from all my patterns that I've recognized, I've noticed that any time you do this next step, the one that gets deprotonated is always the bottom one. Like, it's the one that you just attached. So do you see how this was our alpha beta unsaturated carbonyl and you attached it over here? The part that came from the alpha beta unsaturated carbonyl always ends up being the one that gets deprotonated and does the attacking. As for why, I honestly have no clue, bro. Like, I need someone to drop in the comment section the reason why. So even though this top one is possible, just don't do it. Do the bottom one. So now we're going to go ahead and attack. We're going to attack this carbon and kick this bond up. Now this is going to be a little whack. What I do is just number the carbons involved in the attack or in the ring. So we got carbon 1, 2, 3, 4, 5, and 6. Okay, and just draw a cyclohexane. Don't even worry about all the substituents. Just draw a random cyclohexane and number them however the hell you want. So do 1, 2, 3, 4, 5, and 6. Now you can start adding things. So carbon 2 had the ketone. Carbon 4 had a methyl. Carbon 6 has a methyl, and it also has the O that got kicked up. So now it's going to be an OH. So this was like an intramolecular aldol addition. And then if you were to do an intramolecular aldol condensation, or just the next step, which is dehydration, you form your alpha beta unsaturated carbonyl. So you're going to get this structure right there. This entire set of reaction that we just did is called a Robinson annulation. Robinson annulation is literally just, right, let me write it again. Robinson annulation, step 1, you do a Michael. And step 2 is an intramolecular aldol, where the alpha beta unsaturated carbonyl is the one that attacks. And once again, when I say alpha beta unsaturated carbonyl, I'm just talking about the part that came from the carbonyl that was unsaturated. So that's what you get. Definitely know this reaction because they asked for the whole mechanism on my exam. Let's do another reaction, or another example. So we'll take this, and then we're going to react with, let's see. I recommend y'all also do this on your own if you can. Okay, so this is what we do. The first thing we're going to do is a Michael reaction. So the simple shortcut is to just draw. Well, never mind. We can't do that method anymore. But let's go ahead and number, right? So we're going to bond to carbon 4. We're going to bond to carbon 4. And just finish it as it is, right? So carbon 5 and 6. Carbon 5 has your cyclohexane. Carbon 4 is bonded to carbon 3, 2, and 1. And then carbon 2 has that ketone. That's a shortcut in the sense that I'm not doing the whole mechanism and stuff. So this is my answer after doing a Michael addition. And now we're going to see if we can continue this. So if we were to deprotonate over here, and we attack how many members in the ring? 1, 2, 3, 4, 5, 6. So since we have a 5 or 6 membered ring, we're going to go ahead and do it. So as usual, draw your 6-membered ring. 1, 2, 3, 4, 5, 6. Let me renumber this. I mean, honestly, I'm going to draw the ring that we already have because we already have numbers on them. So we're going to have this little ring that we have. We said this is carbon 5 and 6. And now we're going to draw another 6-membered ring on top of it. So we're going to have something like this. And this would be carbon 4, 3, 2, and 1. And carbon 4 has this little group right here. Carbon 2 had the ketone. And carbon 6 has this alcohol now. And then if we do the heat step, which by the way, guys, for Robinson, you should definitely do the heat step because this one readily dehydrates. So you got this, that, there you go. Moving on, we're going to talk about some other reactions. So if you know like aldol, then the rest of these are like the same thing, but like variations. So Claisen is just aldol, but with esters. So how is this going to look? You got your little carbonyl, and then you're going to get an ester. When you react this with the base, let's not use that. Let's use LDA. you're going to, here, let me draw this again. You're going to attack the carbonyl as you expect, but there's a little difference here. So we're going to draw your acetone, and you bond it to this carbon, which has a methyl. It has the O minus, and it has the OCH3, or just the O methyl. Now, instead of protonating your oxygen into an alcohol, we have a leaving group. And so we're going to reform the pi bond and kick off this leaving group. And as a result, you form this. You basically just formed beta dicarbonyl. Normally, what do we get if we do an aldol reaction? We get something like this, right? We get either an alcohol, or we just get this alpha beta unsaturated carbonyl. But whenever you do a Claisen reaction, you're going to have two carbonyls. And the reason why is because there's no need to make an alcohol. You can reform the pi bond. So that's what would happen if you have a Claisen. Now, Claisens, they can do their own reaction, like your beta dicarbonyls, right? Beta dicarbonyls are pretty, or they have acidic carbons here. Because take a look at this. We have like several alpha carbons. We have one over here. Oh my God. One over here and one over here. The one that's the most acidic is this middle one, because the hydrogen, if you remove it, you're going to get a negative. And look at this. You have resonance from both sides. If you were to deprotonate on the right side, you only have one thing to do resonance with. But if you do it in the middle, you have resonance from both sides. So this is very acidic. And, as you might be able to tell, if you do something like, I don't know, like that, you can just do whatever you expect to happen. So you attack this, kick that off. And that's your answer. Do another beta dicarbonyl reaction. This time we're going to have an ester and a ketone. So to deprotonate this, usually you're going to use a base that matches the alkoxy group of your ester. The reason for this, two things. You're trying to deprotonate this position. So if you use LDA, there's a chance that it will deprotonate this side because it's less hindered. It's not always the case, but I'm just telling you some things that might occur. That's why you want to use something like this where it's not bulky. However, whenever you have something like this that's not bulky, it can also be a nucleophile. But the thing is, if it were to act as a nucleophile, like what are you going to do here? Your ester it contains an OCH3. If you're attacking the ester with an OCH3, do you change it at all? You don't. So you don't have to worry about that occurring. If you really wanted to, you could use a base with a different number of carbons, and I guess they'll let it slide. But in reality, the concern is trans esterification. So that's why it's better to just use something that matches the OR group. But yeah, eventually this will act as a base and it's going to deprotonate this position. And from here, you can do whatever you want. So, I don't know. BR. Next, let's talk about the Decarboxylation reaction. It's basically just an intramolecular Claisen condensation. So let's draw this. And react it with a base that matches our OR group. So we're just going to use that. One of these will get deprotonated, so we'll just choose this one. and it's just going to intramolecularly do a Claisen, right? So you would attack this. Now, obviously, make sure your carbons in your ring are going to be 1 or 5 to 6. So you have 1, 2, 3, 4, 5, 6. So that's going to work. Then I'm going to draw, we'll kick this bond up, draw a 6-membered ring. 1, 2, 3, 4, 5, and 6. And I mean, there's not much else to do here, right? Number 1, you got your ester bonded to it. And then number 6 has the O minus and then the OR group. And we can reform this double bond and kick off the OR group. So ultimately, your product would look like that. Another reaction is called the Knoevenagel reaction, where you're going to have beta diesters, and usually you use a base like a cyclic amine, and this is going to deprotonate your alpha carbon, and then you can do like an aldol with this. So maybe you can bring in a benzaldehyde, and you can attack it, kick this bond up, and then your product would look like this. But do y'all see how it's just like super repetitive? If you understand aldol, you can do anything. There's OH, and then if you were to do the heat step, that's what you would get. Let's talk about using enamines. Enamine aldol. I don't know if this is the name, but I'm going to call it enamine aldol. So say we have a carbonyl, and actually, hold on. Let's do... Guys, the Apple Pencil died again. Ah, man. Okay, we're gonna still do it. So we got this aldehyde and a carbonyl together. We're going to react it with one equivalent of a secondary amine. First, determine what is more reactive. Well, it's the aldehyde, obviously. So we're going to do this. We're going to bond and make our enamine right here. Now, this can also undergo a type of aldol reaction. You're going to look at the lone pair on the nitrogen. It's going to form a bond, and this pi bond will be like electrons, and it's going to bond over here and kick up the pi bond. And let's just ensure we have the correct number of carbons. Remember, this is the carbon that bonded. So we have 1, 2, 3, 4, 5. So that works out. We're going to draw a 5-membered ring. 1, 2, 3, 4, 5. Carbon 1 is bonded to a carbon with an N double bond like that. And then carbon 5 had our alcohol and our methyl. Well, actually, it's going to be an O minus. But how do we protonate the O minus? You use an H plus, right? Or H3O plus. So simultaneously, not only are you going to you're going to protonate your alcohol, your oxygen, you're actually going to hydrolyze this amine. If you remember, anytime you have an amine plus H3O plus, it just becomes a ketone. So you get this as your answer. Okay, let's do one more version of this. This time we're going to do like the Michael type reaction. So go ahead and start with our ketone, and we're going to use piperidine and turn it into an enamine. And now when we have this, we can react with an MVK like that. And remember, we have to choose between the beta carbon and the carbonyl carbon, but since this is a resonance stabilized nucleophile, we attack the beta carbon. So we're going to bring this pi bond down and bond right there. So let's number our carbons. We got 1, 2, 3, 4, 5, 6, and 7. So we'll do this. We formed this iminium. 1, 2, 3. And we're bonding to carbon 4, 5, 6, and 7. So remember that, like, technically you're going to have a situation in which the bond is between carbon 5 and 6, and you have this. Eventually this comes down and this bonds to a proton. But in order for that to happen, you have to have protons present. So you're going to have two things happening. When this inevitably reacts with acid, not only are you going to turn this thing into a ketone, you're also going to hydrolyze this and turn it back into a ketone. So just remember, like, this thing always becomes a ketone or like an aldehyde depending on what it is. So you get that as your answer. Lastly, we're going to talk about my personal favorite, which is, I feel like I say that a lot, but like in this chapter, this is my favorite, beta decarboxylation. Let's get rid of Claisen. So beta decarboxylation, if you have a carboxylic acid and beta to it is a carbonyl, so we'll just draw like that, then you put it under just like literal heat, no other reagents needed, your answer looks like this. So what did I do? This whole group is gone. And I end up with my ketone or my acetone here. Give you another example. Let's do this. Alpha to my carboxylic acid is this, and beta is this and this. One of my beta carbons has a carbonyl, therefore I can just chop this entire thing off, and my answer will be that. In this top example, I didn't label them, but alpha, beta. So you start with the carboxylic acid, and if any of your beta carbons has a carbonyl, it's going to work. Now, how does this work? I'm going to draw it like this. So your oxygen right here is going to bond to the H. This bond comes down, and this is going to break, and this goes up. It's like a whole cyclic cycle. And this only happens when it's beta, just because you form a 6-membered ring transition state. And so as you can see, if you try to like follow along, let's go ahead and like draw it out. So this carbon, this bond right here broke, like the sigma bond between these two carbons broke into a pi bond on this carbon. So you get a pi bond right here. We kicked this pi bond up, so we have a single bond O, which bonded to an H. So we have our enol. And on the right side, we have a double bond O coming in, and that's it. So we have a C, double bond O, double bond O. So this is literally CO2. And on the left side, yes, it's an enol, but it turns into a ketone through tautomerism. And if you just look at it, all we did was we kept this side the same, ultimately. The right side, it left as CO2. That's what happens in a decarboxylation reaction. So if we go into a little biochemistry, the citric acid cycle, or the TCA cycle, or the Krebs cycle, you have this starting material, which is called citric acid, or citrate if it's deprotonated. So this is citrate. And the next intermediate is going to be called isocitrate. So follow along and see what's going on here. Essentially what we did was we moved the OH over there, and this is going to be called isocitrate. So the question is, what was the purpose of this? Well, before isocitrate becomes alpha ketoglutarate, which is the next intermediate, it's going to briefly turn into this, where the OH gets oxidized. I don't know what the hell this is called, but like it's not like an official intermediate. It's like a intermediate of intermediates. The purpose of this is so that, do you see that one of these carboxylic acids is beta to the ketone? It ends up being this top one, because if we look at this one as a point of reference, this is alpha, and we have these beta carbons. This beta carbon has a carbonyl, therefore this gets completely removed. And that is what alpha ketoglutarate is. Alpha ketoglutarate looks like that. That's why this whole isomerization step occurs, so that you can turn the OH into a carbonyl so that it can remove the carboxylic acid up there. Very, very beautiful indeed. This is why I love OChem, because you can understand what happens inside your body. So tough, for real. So with this in mind, just like, I guess like pay attention. Like they could give you an ester and then they'll be like, react it with H3O plus in heat. And they're not going to say step 1, step 2. They're just going to put it together. And sometimes whenever people see heat, they just think like, I don't know, they kind of treat it like a solvent, like it's just there, but it doesn't like really change anything. In this case, obviously nothing's going to happen. Like you just form a literal carboxylic acid, right? The heat could still be there, but it's fine. But then if they give you that, and then they react it with H3O plus in heat, initially you're going to get your carboxylic acid. But since we're under conditions of heat and we are alpha, we are beta to our carboxylic acid, our actual answer would be the ketone. So this is the answer right here. And of course, the other side is gone as a CO2. So just be mindful of that. All right, guys, I think we are done with all of our reactions. I hope I didn't miss anything. And now we're going to do some synthesis practice. So let's see what's going on here. This is going to be like a combination of like everything we covered from the beginning of this video till like right now. So we have some synthesis and we also have reaction practice. There's a lot of stuff. This is going to make this video like 10 hours long. But for synthesis, let's go ahead and start. I see that we have a cyclic ester or a lactone. And how do I make a lactone? Well, I know I have to have a carboxylic acid and an alcohol in the same molecule. And it'll just look a cyclic esterification. So in order to do that, all I gotta do is just reduce my aldehyde into an alcohol. But keep in mind, I have to be a little careful with what I use. Like I can't use LAH because that's going to reduce both my carboxylic acid and the aldehyde. So I use something mild like NaBH4. And when I do that, my carboxylic acid is untouched. Now I have this alcohol. And when this forms a bond and makes the ring, we're going to have 1, 2, 3, 4, 5-membered ring. That's what we have over here. We have our cyclic ester. So use H plus and you get the answer. It's pretty light. Now over here, I actually included this because I saw it on a quiz that somebody sent. But like, this is actually a one-step reaction. You have a carboxylic acid and you can turn it into a ketone. The answer for that is to just use an organolithium with that many number of carbons. So we're trying to add 3 carbons. So you'd use 1, 2, 3 lithium. But let's say we couldn't do that. Let's say they wanted us to specifically do several steps. There's other stuff we can do. So let's go ahead and approach this. There's probably other ways to do it, but like I'm just going with what comes to mind at first. We got diol H. That's going to give me an aldehyde. And then from here, I'm going to do something crazy. I want to make this a nucleophile. So if you kind of remember previously, if we make this dithiane, look what we can do. We can use Bewley to deprotonate that position. Oh, guys, whatever. You guys get the point. You got this. And then you can, how many are we trying to add? We're trying to add 3 carbons. So use a 3-carbon alkyl halide. And then you can extend it. You still got your protecting group added. And then eventually you can deprotect using HgCl2, H2O. That was like one method, right? There's probably a billion other methods, but that's just like what came to mind at first. So that's good. Okay, next thing that shows up, we're trying to go from an alkyl halide into a thioester. So what I'm thinking is I must have made a carboxylic acid and then turned it into my thioester. So I'll just write backwards here. So acid chloride plus the thing we're trying to add, which is that, gives me my thioester. And then to make my acid chloride, I had to have had a carboxylic acid. By the way, you might be wondering, can I go from carboxylic acid to my thioester with that? Technically you can, but like the efficient way is to just make an acid chloride because it's way faster. Whenever you do this thing, where you're going upwards on the ladder from a carboxylic acid, it might not work. It might just go backwards. So that's why generally you'll see in these synthesis stuff that people make acid chlorides. But regardless, we're trying to make this carboxylic acid. Now let me see something right here. We have 1, 2, 3, 4 carbons, and over here we have 1, 2, 3, 4, 5 carbons. So we must have formed a carbon-carbon bond and then got that carboxylic acid. There's 2 ways to go about this. Remember, we can go from alkyl halides into carboxylic acids. The first is by creating a nitrile group. So if we do this, we just formed a bond to a 5th carbon, and then we can hydrolyze this with H3O plus. The other method, which I'll do in blue, would have been to make a Grignard and then react that with carbon dioxide, and that would give you your product, or like your intermediate. And then, yeah. Okay, next we got this ketone, and we're trying to turn it into a carboxylic acid derivative, amide. There's actually, when I made this, I had a different idea in mind, but I just came up with something else right now. We can do MCPBA. And MCPBA, right, the peroxy acid prefers the more substituted side. So you're going to make this little ester. And to go from an ester to an amide, you're going down the reactivity chart, so you can like react as is, you know. And boom, there you go. What the hell is this? So to be honest, it's actually not that bad. But I'm gonna try to work this out. So the first thing I noticed is that we must have had a Robinson annulation occur, because now we have an extra ring that we formed. That's very fitting of this unit. So I'm going to keep that in mind. But this would obviously not be the direct result of a Robinson annulation. I would have to have something like this, where there's a carbonyl present and there's a double bond. But if I put a double bond there, then where does that methyl come from? It can't be part of this because I have 5 bonds. So then the other option might be to put the double bond there. But if I try to do this one, if I try to go backwards, right, when you look at the double bond, oh, by the way, guys, like when you do Robinsons and all this stuff a lot, you're just going to be able to like put pieces together more easily. So I'm going to try to explain my thought process, but it's kind of one of those situations like the more you do it, the more you'll be able to follow along easily. But this double bond is the result of a dehydration, and the alcohol was over here, right? That's just how it always is. The alcohol can't be over here. So if we redraw this, we put in alcohol right here, we know that this carbon got attacked by this carbon, which means that this thing was initially a carbonyl. So I'm going to redraw this again. So this was an aldehyde, and this side we can draw, right? 1, 2, 3. We're saying that this carbon enolate attacked over there to give us our ultimate annulation. So, I mean, this is viable. Like, you could achieve the same result with this method, but then the question is, how do we go from the cyclohexanone to this? That obviously doesn't make any sense. I mean, you could end up doing it, but in this case, it doesn't make any sense, right? I mean, guys, like, if you really want me to, I can tell you how to go from here to here, but that's like chaotic. We're not going to do all that. So we're going to see if the other option works. So we got this, and of course, we know that we can't have this methyl here because there's too many bonds, but I think that I can find a way to add a methyl and remove the double bond at the same time. Remember that we have both this carbonyl and we have this beta carbon. So if you want to use a carbon nucleophile, you have to make sure that it's soft enough to where it doesn't attack the carbonyl. You want it to attack the beta carbon. What do I mean by this? If we used methyl magnesium bromide, this is considered a strong nucleophile or a hard nucleophile that would attack the carbonyl. If I had an organolithium, same deal, it would attack the carbonyl. But what is something we know that's weaker than these? It's going to be our organocuprates. So we got this. This would attack the beta carbon. And if we do that, we're going to shift this bond over here and shift that up there. And what would that give us? So we get an O minus up here, whatever, and a double bond, and this methyl right here. Now, of course, like, there's always going to be a workup protonation step. And when you do that, technically you get this enol, but you turn that into a keto, right? So what is that going to ultimately give you? A methyl and a ketone up there. And we know how to go from this to the final product. Just use a reducing agent like NaBH4 or LAH. Okay, so let's write this step in again. All right, now we just have to ensure that we can do this Robinson annulation, like go from here to here. So same deal, if I try to work a little backwards, I know that this double bond meant that there was an OH right here. Once again, it cannot be over here. That's not how it works. Because how would this attack over here? It doesn't make any sense. So when we redraw this, we have our OH right here. And what we're saying is that this attacked what was initially a carbonyl or a ketone. So we're going to separate them and turn them back into what they were initially. So over here, we got the carbonyl. And then this little pink side is still attached from this bond, right? So we'll draw a bond, and what is this? 1, 2, 3, 4. So 1, 2, 3, 4. and we have this carbonyl right there. And once again, we are saying that this outer carbon attacked over here to form our ring, right? If we renumber it, 1, 2, 3, 4, do you see how 4 is what attacked this carbon to kick that bond up? And this definitely looks attainable easily because we have this cyclohexanone like right here. So all we're trying to do is add this guy in green. And how do we do that? Obviously, I noticed that we have a carbonyl still retained. So instead of doing an aldol, I did a Michael reaction. Obviously, like you should know that you have to do a Michael at first. Otherwise, you can't do a Robinson. So that's like a giveaway. But we did a Michael reaction, and this thing is what we reacted with. Just draw as is, and don't forget your alpha beta unsaturation. So this is your answer. But of course, like the very first step is to deprotonate, and then you got this, and then so on. Now this next one looks even scarier, but if you understand what we just did, it will be very easy. So the first thing I'm going to do is I'm just going to reorient this molecule because I see that this little cyclohexane with the methyl is on this side. So if I redraw it, we get this, and then we got that. The next thing I'm going to do is kind of see like where this double bond came from. So the double bond must have come from an alcohol that was on this position. So we must have had something like this. And same deal as last time, this carbon formed a bond over here and kicked up the pi bond, right? So initially we must have had this structure. I'll call this 1, 2, 3, 4, 5, and 6. So this would be 6. This is 5. And then we got 4, 3, 2, 1. Carbon 2 had the carbonyl. And then carbon 1 is what attacked. And then from here, we can just finish off the molecule. So carbon 4 is bonded to this whole group. Forgive my drawing. Let's erase all these. So we made that. So now all we got to do is go from this to that. Now I realize my reorienting did not help because now it's even more confusing. So I'm going to reorient it again. I'm just kidding. I don't need to because all I can see, I'm going to highlight it right in green. This was our starting material. And what are we trying to do here? We're trying to bond this cyclohexane, this blue cyclohexanone, to our green molecule. And as you can see, our green molecule, which is now purple, has this double bond. So it must have been the alpha beta unsaturated carbonyl in the Michael reaction. So how do we make this? Just include your pink molecule, which is your enolate, which is the cyclohexanone enolate. And so it would attack over here, kick this around, and you'd end up with this structure. So it ended up being like the same as the previous one. Okay, moving on, we're trying to go from an ester to an enamine. And so our enamine, we know that we can make enamines from carbonyls, so we're going to do that. We're going to start with the carbonyl right before this. And in order to make that enamine, you're going to have a secondary amine. So now we got to figure out how to go from a ester to a ketone. So something powerful we know how to do is going from a carboxylic acid to a ketone. So the first thing we can do is turn this into a carboxylic acid. You can just hydrolyze it with acidic water, and that will give you your carboxylic acid. And all you got to do from here is replace the OH with 2 carbons. And we know how to do this now, which is using an organolithium with 2 carbons. Remember, do not use MgBr or CuLi. These are not going to work. You're going to use this, and there's your answer. Lastly, we have ethanol to acetonitrile. So both of these have 2 carbons. That's good to know. What I'll mention is we only know one method of making a CN. Obviously, we know about substitution. Like, you guys know about this, obviously, where you can react with the CN and attack. But the problem with this is you're introducing a whole nother carbon. In this case, we have 2 carbons, we have 2 carbons. So it seems like this carbon I'm pointing at in purple is this one. So we can't do an SN2. So in that sense, there's only one thing we know how to do to make a CN, which is POCl3 or P2Cl5. And what reacts with this? It has to be an amide. So we got to go from this ethanol to this acetamide. How do we do that? First, we're going to make a carboxylic acid. So strong oxidizer. And from here, it's a light work. You can go directly to the amide, or if you want to be more efficient, you can use SOCl2 to make an acid chloride and then react with the thing you're trying to attach, so NH3. Now we're going to do some fun reaction practice. So SOCl2 is going to turn our carboxylic acid into an acid chloride. Now this next step, we have this diamine reacting. Now there's like many ways you could go about this. My first thought is maybe you have one of these reacting with that, and then you have a completely different one reacting with that. That could be a valid option. But another thing I'm thinking is maybe we attach this over here, and then this part of the molecule attacks over there. That's like another viable option. If you said one or the other, you could be correct technically. But over here, they gave us a formula. So you can try one method. If it doesn't match that formula, then try a different method. I'm going to make it simple and just do the correct answer. But once again, if you said a different option, you could technically be right. It's just that for this specific question, it's not. So we'll go ahead and start. What happens here is you're going to have one of these reacting, and you're choosing between acid chloride and an aldehyde. If you had to choose between the two, acid chlorides will react more, or they'll react faster, because acid chlorides are super reactive. They're one of the most reactive things you learn in all of undergraduate organic chemistry. So we're going to react with our acid chloride and essentially turn it into an amide. So this chlorine will leave and you made like an amide. And so what this is going to look like is this. So your aldehyde is still intact. Now you bond it to one N, but you have this whole R group which has another amine on it eventually. Now we know that amines and carbonyls react, and we have both a carbonyl and an amine. So now this will do an intramolecular reaction. We have a primary amine and a carbonyl. Primary amine plus carbonyl equals imine, which is the double bond nitrogen. So this is going to react over here, and of course stuff will happen, whatever, and you're replacing this with the nitrogen that you're bonding to. So what we're going to do is form a ring, and it's going to be a ring like this, right? So we're going to count all the atoms inside of this ring that we're trying to make, so it'll be easier. So we got 1, 2, 3, 4, 5, 6, and then 7. So we're going to make a 7-membered ring, and I always just draw the ring from scratch. I don't try to like match up atoms or anything, just draw a 7-membered ring. So we're going to do that. So bear with me while I attempt to draw a 7-membered ring. Yeah, this is fine. And then we're going to number the positions in whatever way we want. So we'll do that. And then let's start matching things up. So, guys, this is pissing me off. I'm not going to lie. Let me draw it again. There we go. All right, 1, 2, 3, 4, 5, 6, and 7. All right, what do we got here? So number 4 is going to be a nitrogen. So we're going to replace this with a nitrogen. Carbon 3 has the double bond O on it. Number 7 is also a nitrogen. And number 1 does not have this carbonyl anymore. Remember that we're forming an imine between atom 7 and atom 1. So when you draw the double bond, it should be between carbon 1 and the nitrogen. Make sure not to draw your double bond over here, because that's a completely different carbon. So you're going to draw it like this. And this would be your answer for that box. So we're going to go ahead and erase this. So 7-membered ring with both an amide and an imine. And if you try to verify this with our formula, you'll see that it works, hopefully. Now we have LAH. Remember, when you have LAH and an imine, you're just going to turn it into an amine. And if you have an amide plus LAH, you're just chopping this off and keeping it as an amine. This is different than like esters and carboxylic acids and stuff like that. If you had a carboxylic acid and you react with LAH, you're turning it into an alcohol. If you had an ester and you react with LAH, you make the same thing. That's like the case for like all of these derivatives. But when it comes to amides, you're actually turning it into an amine. So you would just chop this off. So we're going to keep that in mind. I'm going to go ahead and copy and paste this ring because I don't want to draw it again. And so first, the amide, chop it off. And by the way, guys, I forgot the H. Sorry. So there's that. And then when you have an imine, you just remove the double bond, replace with hydrogens. So this will be our answer. Now lastly, it says to use an excess of methyl iodide. And so this is that example of exhaustive methylation. And so the first thing that happens, your N has a lone pair, so it would bond to the methyl and kick off the iodine. And both of the nitrogens will do that, right? So when we draw this, you're going to have one bond to the methyl. You still have an H, and it's positive. And the same deal for this one. But remember, it's called exhaustive methylation. So you're going to max out your bonds to carbons. And we have hydrogens present. What ends up happening is that the hydrogens go away. You get deprotonated. And that leaves room for an additional bond for both of the ends. So this is going to react again. And eventually, you're going to get this, where you maxed out the methyls. So remember, if you have H's on the end, just remove them and attach another methyl. This is our actual answer. This is the result of an exhaustive methylation. Now, this is like the last of this question. They didn't ask for the next step, which is to do elimination. But we're going to go ahead and do the Hofmann elimination. Right? How do we do that? Ag2O and H2O. Or alternatively, never mind. You do Ag2O and H2O. Over here, we have, let's start with the top one. We want to eliminate this one. You have two hydrogens to choose from. So let me bring it over here. Okay, you can choose over here or over here. Honestly, it doesn't really matter, but technically this one is better just because it's further away from this nitrogen, which is really bulky. And so you want like the least steric hindrance. So technically this is the better position, but our base, which is a hydroxide, will come in, take this to form a double bond, and simultaneously you kick off this leaving group. So when this first elimination happens, you're going to get this. We're going to get that. And then we're going to do it again. Bro, I hate this app. Okay, we're going to do it again. Now we're trying to remove this bottom one. You have two options. We have one over here and one over here. The thing is, even if you tried to remove this one, there's nowhere to form a double bond because you already have a double bond here. So you can't form a double bond here. So even if this tried to get removed, it wouldn't lead to anything. So we know for sure that we're going to remove this hydrogen. So let's continue that. We're going to have our base, extract this, form a double bond, and kick this off. And we're going to end up with two products. This is the first one, and this is the second one. Next up, we got CH3N2 or NH2 in excess. So we have this methylamine, and we have both a ketone and an ester. So the ketone we know is going to become an imine. So I'm going to draw that. I'll keep the ester intact for now. So we're going to draw an imine right here. And now when you have an amine plus an ester, since you're going down the reactivity chart, you're going to turn it into an amide. So this would attack over here and this would break off. Okay. And so when you do this, you have that with your amide now made, and the rest of this just draw as it is. You have your O, which became an alcohol, and then you still have your amine right there. So you're reacting with both of them. Over here, H2O2. So this is like the Hoffman elimination, right? So the first thing that happens is that your N gets bonded to an OH, and now it's positive, and then you have a base present. And since this whole thing is like really bulky, it's going to do a Hoffman elimination. And so it can extract from, I guess, like 1 or 3 places. You can extract a proton from here, here, or here. I'm pretty sure. So the answer is that you take it from here. I think it's just that like there's a lot going on over here. Even though these are all primary positions, these are like kind of stacked up on each other. And you know that they're stacked up on each other because the connection point is here. And so you can definitely know for sure this is stacked, but over here it's more free. And so you take this hydrogen off and you're going to break that up when you form a double bond. And so as a result, you're going to get a 5-membered ring. So see, this is 5 members, right? Yeah, it's 5-membered ring. So you're going to have a 5-membered ring with an N, and you have your OH, and then it's carbon 1, carbon 2. Carbon 2 is what's bonded to all that stuff, so it's like what? A, B, C, okay. And then between B and C, you have your double bond. So that's our answer. Okay, next we have this. So step 1 is going to be reduction. So you're going to get this, and as you can see, if we just draw it differently, we get this. So it looks like it's going to be a protecting group. And what's our next step? Our next step is this. It has a ketone and an aldehyde. And so what do we react with? We react with the more reactive thing, which is the aldehyde. So we're going to essentially protect that. So the next step would be to draw this, and our aldehyde is protected. So we got this. Can't draw for my life. Something like that. And then we got our Grignard. So the Grignard will go ahead and attack this one to give us our alcohol with 3 carbons. And then I'm not going to draw this protecting group again because we know we're going to remove it, right? So ultimately, this becomes an aldehyde again. Okay, H plus NH2OH with LAH. This one is pretty simple. What happens at first? You're going to make this oxime. And then with LAH, you turn it into a primary amine. So this ends up becoming that. Okay, we got a dithiene or diacetyl protecting group. And so, I mean, there's only one thing to protect, which is the ketone. So we're going to start with that. And we have our CN. Now we have LAH, and so LAH will reduce the CN into a C bonded to an NH2. So with LAH, you're removing that triple bond and just making it single bonds. Make sure your carbons are counted properly. So we have 3 carbons here. So we're going to have 3 carbons, 1, 2, 3. And this third carbon is bonded to an NH2. At first, this C was triple bonded to the N. Now it's CH2, NH2. So we have that. Now this HgCl thing is going to deprotect us. So we get our ketone again. And lastly, it says H+. So I have an amine and I have a carbonyl. And this is a primary amine. So I should form an amine. And let's just count how many members will be in the ring. 1, 2, 3, 4, 5, and 6. It's going to be a 6-membered ring because this is going to go over here, right? And then we're going to turn that into an amine. So your answer would look like this. I don't know if I can number properly. Let me just draw it like this. And then this becomes a nitrogen and double bonded into an imine. If I want to make it into an amine, you just use LAH, right? So you can go ahead and do that. And you get that. Next, we got H103, H2SO4. Okay, so remember, this is kind of like a deactivating electron withdrawing group. And so you want to be placed meta to this. So how are we going to do that? Oh my god. Just know this is ortho and this is meta. This is ortho, this is meta. So we're going to draw that. We'll just do it on this side. So we got our NO2 over here. Now, nano2HCl. This must have been a mistake because you can't use nano2HCl on an NO2. You have to turn it into an amine at first. So let's draw step 1.5. 1.5 is to turn it into an amine. So ZnHgHCl. That's going to turn you into an amine. Now, when you do step 2, nano2HCl, that will give you your diazonium salt. H2SO4 is going to turn it into an alcohol. And now, lastly, we have this anhydride. So we have an alcohol plus an anhydride. It's not that hard. All you got to do is react with it and make a carboxylic acid. So this would like attack one of these and then kick off the other group. So when you draw your product, it should look... How does this ring get worse and worse every single time? It would look like this. And as a byproduct, this thing would also be its own carboxylic acid. Also, I'm stupid. I meant to say you make an ester, not a carboxylic acid. But that's what you would get. Moving on, we have what appears to be a Dieckmann reaction or an intramolecular Claisen condensation. And so we have our base over here, and we have a couple options of deprotonation for alpha hydrogens. So we can either do this one or we can do the one in blue. If we do the one in blue, we're going to make, let's see, 1, 2, 3. We're going to make a 7-membered ring. If we do the red one, it will just be 2 less, which is 5. So if you're choosing between 7 and 5, you go with 5, right? 5 and 6 are the ideal ones. 7 is acceptable, but it still has some ring strain. And of course, 4 and below is also like trash. So since we're choosing between 7 and 5, just go with 5. So we're going to pursue the red anion. And just do your little attack, right? We can go ahead and number this. So we got 1, 2, 3, 4, 5. And remember, like when you attack, this pi bond goes up, but then it goes back down and kicks off this OCH3. That's something we know by now. So we're going to draw our product. We have a 5-membered ring. So we're going to number this 1, 2, 3, 4, 5. Carbon 1 is bonded to these 3 carbons with an O, and then carbon 5 reformed its pi bond, so it looks like that. This might have been the example that we did, I don't remember, but something like this, right? But that's what you're going to get for your product. Okay, what happens over here? As you can see, we have one single molecule reacting with heat. Whenever you see something like this, it's very obvious you're doing an intramolecular reaction because the only thing you're reacting with is literal temperature. So yeah, that's something to keep in mind. We got a thioester and we have an amine, and an amine can react with the thioester because we're going down the reactivity chart, so that's gonna work. So we'd have our amine attack the thioester, and then the usual, right? You kick the pi bond up, it goes back down, and you kick off the sulfur. So to keep it simple, I'm just going to draw an arrow kicking off the sulfur. Now, this is going to look very, very blasphemous to all of organic chemistry, but I promise I'll fix it. But here's the thing, right? We got carbon 1, 2, 3, and then we have our nitrogen. So I'm going to draw 1, 2, 3, carbon 1, 2, 3, which is bonded to an N, which is bonded to this carbon. I'm sorry, guys, I had to do it. Carbon 1 is bonded to this sulfur, which is now a thiol. So obviously, this looks whack, but we just formed like a little cyclic, this is like a lactam, right? We formed a cyclic amide, and now the S got kicked off. But what is something you notice? Do you see how initially we had a cyclic thioacetal, and then we had this 3-membered substituent? Now we made a cyclic amide, and we have this 3-membered sulfur substituent. So if you want to draw this in a better manner, you can literally just replace the S with the N, and like you can swap them. So yeah, we're gonna do that. So you got this, and kind of see that, right? This is going to be 3, 2, 1, and it's bonded to this group right there. So that's what happened here. Okay, next we got CH3ONA. We got a little nucleophile here, and we have this anhydride. And so here is the thing. You can't just attack one or the other and say they're the same thing, because when you attack an anhydride with an alcohol or like an alkoxy group, one side, like let me just draw it over here. So you have an anhydride, and you're reacting with this. One side will become an ester, and the other side that had this as the leaving group is going to become a carboxylic acid. And so depending on what reacts with this alkoxide, you're going to get a different answer. For example, one answer would be that, and the other one would be to just flip it, right? So you can put an OCH3 here and an OH right there. So they're clearly not the same answer. It all comes down to leaving group stability. So if you were to attack, which side of the anhydride is more reactive? Let's say that this left as a leaving group. You'd have O minus and you have a Cl. And now let's talk about the other side, leaving as a leaving group. Which one is more stable? The only difference is the left side has a chlorine and the right side has an iodine. And these are acting as inductive effects. So when you look at your periodic table, you want the more electronegative one when you're talking about inductive effects. So since chlorine is higher than iodine, chlorine is more electronegative, which means this is more stable as a leaving group, which means that when you attack, you're going to attack this side and kick this off as a leaving group. And so ultimately, the side that becomes the ester is the iodine side. So you're going to have that. And then let's draw the second product, which is on the left side. You're going to have a carboxylic acid. So, this is where it's important to like understand the concept rather than just memorizing, because clearly you can't just choose one or the other. You have to choose a specific one. Moving on, what do we got here? Okay, another protecting group situation. We have an aldehyde and ketone. We'll protect the aldehyde as usual. So let's go ahead and do that. And then we have KCN, which is just negative CN. CN plus a carbonyl equals a cyanohydrin. So we got our OH, and we got our CN right there. And we still have a protected group. Now we have H plus H2O. You might think that this is our answer, but don't forget CN plus acidic water equals carboxylic acid. So your actual answer would look like this. This is our answer. Okay, moving on. Let's see what we got. So, honestly, I was like tweaking out for a second. Yeah, I was like, what the hell is going on? Remember what I said? They're not gonna ask you to put a deprotonated species as your answer. I mean, they could. If it's a whole reaction map like this, they could. But I was just thinking right now, if this was my answer and I'm reacting with base again, what's going to happen? This is very clear to me that we're reacting two of these white molecules together. So let's do that. We're going to have two esters. And let me just draw the other one over here. One of them got deprotonated, so we'll do this one. And the other one is going to be attacked. So we're going to attack this. And then just to keep it simple, we'll say that this leaves. Okay, now when we draw our product, we'll keep the attacking molecule the exact same. So we're going to have, and we bonded to, we carbon 1, 2, 3, 4. So we bonded to 1, 2, 3, 4. Bro, why does it always do that? 2, 3, 4. And carbon 1 had this. So we just made like a little dicarbonyl right here. And I'm gonna redraw it by putting this over here and making this 2 carbons. But it's the same thing. Now we have this base, and it's going to deprotonate this central carbon. You're always going to deprotonate that part. So we'll go ahead and draw this. And we're going to attack over here and kick that off. Okay, really quick, I need to clarify something. I said you're always going to deprotonate the central carbon. The only time you wouldn't do that is if you're under kinetic conditions. So if you were to do like LDA negative 78, then you can say, okay, I deprotonate this position. But if they don't specify anything at all, just always do the central carbon, okay? So now lastly, we have H plus H2O with heat. So that is going to hydrolyze my ester and turn it into a carboxylic acid. I still have this. But don't forget, we have heat. And what do I have right here? Carboxylic acid, alpha, beta to it, I have a carbonyl. Since the carbonyl is beta to the carboxylic acid, just chop it off. And that's my answer. For the next question, we have what looks to be very scary, but all you're doing is hydrolyzing each of these carboxylic acid derivatives. So what that means is that you're going to replace leaving groups with OHs to make carboxylic acids, right? So in this first one, this ester, we're going to chop this off and replace that whole OR group with just an OH. Now, this O, it left. So it's just going to be OH after it gets protonated. So we got that. Then we can continue. Same deal here. We're going to chop this N group off and turn this into carboxylic acid. Now the N just becomes an NH2. Continue like this. And now we have an anhydride. The thing about anhydrides is that you have two options for leaving groups. Option 1 could be that this right side left, and option 2 could be that this left side left. When it comes to hydrolysis, it doesn't really matter if you incorrectly identify the leaving group because both sides turn into the same thing, which is a carboxylic acid. But you still should know, because if they give you a different reaction, like they want you to react with an alcohol, you have two options of what can be made. If you claim that the right side is the leaving group, then you're going to get the right side as the carboxylic acid, and the left side will turn into the ester. And if you do the opposite, then the left side will be the carboxylic acid, and the right side will be the ester. So obviously, these are different scenarios or different molecules you can get. So you have to know what's the actual leaving group here, because it will impact your answer. And in order to determine that, let's say that the right side left. What would we get? We would get this. And then let's say the left side left. What would we get? We would get that. Which one is more stable as a leaving group? It's going to be the purple one, because you have a withdrawing group right there. For the left side, you have this whole R group, which is all donating, which is not good for negative charges. Therefore, we know that the leaving group in this anhydride was this whole thing. So this whole thing left. But as I mentioned, in this case, it doesn't matter because both sides will become OHs. So over here, this becomes HO, and then you continue it, and you're done. So that is our answer. And then lastly, we have this. We have a primary amine, and we have an ester. That's the only thing I can react with. So I'm going to react with that, right? So you're going to react with it, and eventually this breaks off. But it's still part of the overall molecule because it's a ring. But it's just going to become an alcohol, while this thing becomes an amide. So what is that going to look like? So this is now an amide. And down here, we have the alcohol, double bond, and that. So this is the answer, but technically the better answer would be to turn that enol into a keto, which in this case is going to be an aldehyde. Right, you see this right here? This is an enol, so technically you should turn it into a carbonyl, but if you didn't notice this or you just forgot, it's fine. I don't know if it matters that much. Okay, now we're going to get into some ranking. So there's only 3 types of ranking I have. There's many like versions of them, but 3 main types of ranking. One is just about reactivity, the other is acidity, and then we have basicity. So I gave a couple examples, but if they ask you any variation of it, it's pretty much asking the same thing. For example, this first one, it's asking about ranking by hydrolysis reactivity. And if you pay attention, you see that we have some carboxylic acid derivatives like esters and thioesters. They can easily change this word hydrolysis to something else. Like they could say rank by saponification reactivity, or I don't know, I can't think of any other names right now, but rank by something reactivity. Even if it's like a name you don't know, if you see that we're ranking carboxylic acid derivatives, it's going to be the same thing, which is just ranking by their reactivity. So remember that the more stable the leaving group, the more reactive the derivative is. And as you can see in this case, we're reacting 2 types of derivatives, just thioesters and esters. If they give you all 5 different derivatives, that's really easy, but we're reacting the same 2 derivatives here, which is where knowing how this works will make it much easier. if you remember why the ranking of our carboxylic acid derivatives exists, then you can answer this question. Remember that the reason like an acid chloride is really good is because the leaving group chloride ion is super stable compared to something like that. So in this case, just check your leaving groups out and see what's the most stable. So our leaving groups will be these, right? So like an S minus, we're going to have an O minus again, and that. Now remember, we're going to go by my method, which is areo. So areo, the atom, I already talked about this in case you already saw that part, but if you didn't, I'm going to explain it again really quickly. But A is going to be atom, and so if you're comparing two elements in different groups, like you're comparing N to S, the S will always win. If you're comparing P to S, the S will always win, because you want to be more electronegative or further to the right. If you're comparing Cl to like N, the Cl will win. But we're comparing O's and S's. O's and S's are in the same group. So generally, you want to go downwards, right? You're going to say that S is better than O. But if you have resonance and you're comparing two atoms of the same group, the one with resonance will win. So, for example, an O minus is better than an S minus if the O minus has resonance. But if I were to bring in the S with resonance, then of course it's better, because both the S and the O have resonance. So since they're the same, you go with S, which is better. In this case right here, you have O and an S. Sure, S is generally better, but the O has resonance and the S does not, so the O is better. And then like lastly, you would have the O without resonance. So we're going to keep that in mind when we're doing this. And of course, if everything is the same, then you can look at inductive effects, which will show up in this question. So I have S, O, O, S. Okay. So as you can see, the first and the fourth molecule have S with resonance. So these are going to be my top two, because you can't beat S with resonance if you're in the same group. The first molecule has an extra NO2, which is pretty good because it's an electron withdrawing group. And this one does not. So we're going to say this is rank 1 because it's the most stable. And this will be rank 2 because it's still an S with resonance. Now if we compare the second and the fifth molecule, these are going to be O's with resonance. And this third one is an O with no resonance. So this is going to be rank 5 because it's just like the worst. Now if we compare the second with the fifth molecule, I see this molecule has an extra methyl, which is electron donating group, which is bad. Whereas this last molecule does not have such a thing. So it's going to be better than the other one, meaning this is rank 3 and this is rank 4. All right. Rank by reactivity of the carbonyl compounds with a nucleophile. Same deal here. They could word it differently. They might be like rank by rate of hydration, or they'll be like rank by rate of cyanohydrin formation, or rank by formation of hydration product, or something like that. Or like the amount that's produced. If you don't know what the hell they're asking, but you see this right here where we have a bunch of ketones and aldehydes, then you're going to know like, oh, I'm just ranking by the reactivity of the ketones or aldehydes. Like, you don't have to know what reaction they're talking about. It's going to be the same thing, because what else are you going to rank these by? The only other thing you can rank by is like acidity, but they're not asking about acidity, they're saying reactivity. So remember that your carbonyls are partial positive because of the dipole moment going up. And so if you do something to stabilize your carbon, such as providing electron density through electron donating groups, you're not going to be as reactive as something that has nothing, and you're not going to be as reactive as something that has electron withdrawing groups. Because if this is partial positive and you're withdrawing electron density, you're making this extra partial positive, which means it's desperate for a nucleophile to come in and attack it. Over here, it's not as desperate. It's partial positive, but it's not as desperate as this one. So you want to kind of keep those factors into consideration. So let's see what we have. On the left side, we have 1 electron donating group. Over here, we have 2 electron donating groups. We have nothing. Over here, we have 1 electron withdrawing group. Over here, we have 2 donating groups. And over here, we have 2 electron withdrawing groups. So withdrawing groups, right? 2 electron withdrawing groups is better than 1 withdrawing group is better than nothing, is better than, right? Like this, for reasons we just talked about. So we can easily rank this as 1 and this as 2. This one will be 3 because there's nothing. And then this will be ranked 4 because it's 1 donating group. Now between the remaining 2, the only difference is that this molecule has more donating effects because it has a big group. It's also like sterically hindered low-key. So this will be really bad. So we'll call this rank 5 and this will be rank 6. All right, rank by acidity. Most acidic is rank 1. So I know we've done acidity like all the way back from OChem 1 and we've seen it in many variations, but that's the thing, right? It just keeps showing up in different variations. You might or might not know the answer to these, so we're gonna go ahead and talk about them because OChem just keeps changing for real. So, of course, the first step, as always, is going to be to deprotonate the most acidic, hydrogen or the most acidic carbon. And so we're gonna deprotonate over here. Over here. This one will be over here because you can't do anything on this side, and there's nothing over here. We have a hydrogen right there to remove. And then this one's kind of interesting, right? You might think it's like over here, but we have an alcohol present, so it's actually going to be right there. Okay, so here is the thing. Normally, alcohols are more acidic than a regular like carbonyl, like a ketone or aldehyde. But if you have a beta dicarbonyl, it will actually be more acidic than the alcohol. So I'm going to deprotonate and put a negative here. I'll put a negative and negative. Right? In a regular carbonyl, you can resonate with the oxygen, but it's not as stable as the O just being on the negative to begin with. However, in this case, since you're able to resonate with 2 oxygens, it ends up stabilizing it more than what you had over here. So that's something you want to consider. So I have 2 molecules here that have beta dicarbonyls. And of course, the difference is that this one has an extra electron withdrawing group, which is good for negative charges. So this will be rank 1, and this will be rank 2, and then the O will be rank 3. And then between the remaining 2 molecules, this one is still resonance stabilized with the carbonyl, so it'll be rank 4. And this one has nothing, it's just a primary, so it'll be rank 5. Next, rank by acidity, and this time we got a bunch of different molecules. So it's also kind of whack. Just it's kind of one of those things, like I'll probably include it in the description of this video, but it's not always that carbons are like the least acidic, as you just saw. It kind of like depends on what you're dealing with. So carboxylic acids are going to be like usually like the most acidic thing you're looking at. Then you can bring in your beta dicarbonyls, and then you can bring in your alcohols, and then regular carbonyls, and then your alkynes, and then your amines. Don't really have much to say about why this is the case. You can make a bunch of arguments for like all of these, so I'm just gonna like not do that. you know. I guess one more thing I want to mention, technically, if you had a thiol, it would be right here, like above the beta dicarbonyl, but, you know, caveats may apply. So this is kind of like something you kind of just like know it or you don't. I guess keep in mind that your terminal alkynes are more acidic than your amines. So it's weird for real, bro. It goes from O to C to O to C to C to N. So yeah, once again, I'll attach the pKa chart on in my description. But I guess knowing this, we can do our ranking. So this would be rank 1. Next we have our O, so rank 2. Right, I'm looking at this, by the way. And then we have our carbonyl, so rank 3. And then we have our alkyne, so rank 5. And then we got this. All right, rank by acidity again. Now this one is a different case. So we have all these benzoic acids. It's just a benzene with a carboxylic acid. But we have different substituents on the benzene, and they're either not there or they're going to be para. So I'll tell you the general thing, okay? Ortho and para substituents have the most prominent effects, with ortho being better than para. So what does that mean? If you're looking at like a single substituent, electron withdrawing group ortho is better than electron withdrawing group that's para is better than electron withdrawing group that's meta is better than nothing. And then it just like flips, right? This is going to be better than electron donating groups that are meta is better than donating groups that are para is better than donating groups that are ortho. I'll tell you why. If we look at like, well, first of all, remember, like we're ranking by negative charge stability. And so if you look at this right here, right, we'll take this donating group that's para. Whether it's para or ortho, you can get the same resonance structures. So this can donate like that. And you ultimately end up with a negative charge right here. You don't want two negatives next to each other because they're going to repel each other. That's like not stable. But if you take NO2, the NO2 can take this, and this will come over here. You end up with a plus right there. And plus and negative is very stable. So the only difference between ortho and para is simply that you're going to be closer to the electron withdrawing group if you're ortho. So that you'll still get the same deal over here. We get a plus, but you're closer to this NO2. So it has a little stronger effect. And then meta doesn't have the positive showing up right here. So that's why it's not as good as ortho and para. But just simply being near an NO2 is still good. That's why it's going to be better than if you have like nothing, you know? And then same deal for an ortho donating group. You can donate and kick this up into a negative charge. Now you have two negatives next to each other. It's not good. And you're also next to this donating group, which is extra bad. That's why it's like the worst situation to be in. If you are meta to your donating group, you won't ever get the negative charge right on this carbon. That's why it's going to be better than being ortho and para. But it's still bad. All right, so now that we know all this stuff, we can go ahead and rank. So I don't have to worry about ortho and para right now, or even meta, because everything is either para or just non-existent. So we're just basically going by strength of the donating or withdrawing group. So NO2 is generally going to be our best. So this will be rank 1. Then we have Br, which is going to be rank 2. Now we're left with methyl, OCH3, and nothing. So nothing is better than something bad, so this is rank 3. And then between methyl and OCH3, OCH3 is a stronger donating group. So this is going to be the worst, rank 5, and this will be rank 4. Okay, now we got acidity, but we have substituents moving around. So if you use the same trend I just showed above, that will make it much easier. So we have an NO2 that's ortho. We have it meta over here, and we have it para over here. So this will be rank 1, rank 2, rank 3. And then we have 2 alkoxy groups. So remember, meta is going to make it weaker affecting than if it's like ortho or para. So this will be next in line because it's not as prominent effects, but this one has very strong negative effects on it. So that would be our ranking there. Guys, it's been like 10 hours of recording or something, so if I make some stupid mistake somewhere down the line, please grill me in the comment section. Lastly, we are here with amine basicity. We talked about this in the beginning, so yeah, it should be pretty chill now. Remember, the first step is to look at the N hybridization. And sp3 will be better than sp2 is better than sp. So we're going to go ahead and classify them. So this will be for the N. This will be for the lone pair if needed. So the N over here is going to be sp2 because of resonance. It's going to be sp. Over here, it's sp2 because of resonance. sp2, and then this is sp3. So we can rank a couple of these, right? We have only one sp3, so this would be rank 1, and we only have one sp, so this would be rank 5. So we're comparing 3 sp2s. The next thing you look at is the lone pair hybridization, and so sp2 is better than p. So let's take a look. Since this lone pair can participate in resonance, it's going to be in the p orbital. So this is going to be in the p orbital. Same deal with this one. Since it can participate in resonance, it's going to be in the p orbital. And over here, the lone pair has no resonance it can do, so it would be in the sp2 orbital. So sp2 is better than p. We have only one sp2, and we have 2 p's. So we can say that this is rank 2. Now, lastly, we can look at quality of resonance. So this resonance, if it were to resonate with the benzene, it would be really bad because the benzene is aromatic as it is. And so if you were to resonate like this, you're disrupting the aromaticity. It's not the most ideal situation. So we'll keep that in mind. We'll say bad resonance. This one is pretty good resonance because you're resonating a negative charge on the oxygen. So that's pretty good. But remember, good resonance equals bad basicity, because if you have good resonance, this lone pair is busy being unavailable, which means it can't bond to something. So that actually means that this bad resonance one is rank 3 because it's more available lone pair. It can just bond to something else because it's not busy resonating with the benzene. And this would be rank 4. And remember, guys, there is one more thing you could check if everything was the exact same, which would be inductive effects. So let's look at this. If we were comparing this and we added an additional molecule, the only difference is that this has a methyl, and that's extra. So what you can do is look at the protonated form, so CnH+, and just look at which one is more stable as a positive charge. Since you have an extra donating group, it would stabilize and make this, more basic to begin with. So this would have been the true rank 5, and this would have been rank 6, if you were to compare these two. Two final things that I feel like I forgot to mention, or maybe I mentioned but was not emphasizing enough. The first one is with your carboxylic acid derivatives. If you're trying to go up the reactivity ladder, let's say you're trying to go from an amide into an acid chloride. If you're trying to go upwards, you have to convert into a carboxylic acid. I feel like this is kind of obvious, but I didn't really mention it too much as far as I'm aware. So if you have this amide, simple, just hydrolyze with the with acidic water, and you make a carboxylic acid. And then from here, you can make your acid chloride with SOCl2. If you have an ester and you want to turn it into an anhydride, first thing you do, hydrolyze, make your carboxylic acid. And then, of course, technically, carboxylic acids can become anything. Like, I can directly create this, but the preferred method is to convert it into an acid chloride, so it's super reactive, and then you can react with whatever you're trying to add. But once again, technically, you can go directly from here to here, like that. Okay. And then the second thing, I think I just mentioned this pretty recently, but I'm going to mention it again because I don't think I emphasized it enough. So we talked about thermo and kinetic conditions. Just don't worry about those unless they specify. So if I gave you this, or let me low-key extend it. If I gave you this and I said to deprotonate it, you're going to always deprotonate this position. However, if they decide to specify the temperature, which is kinetic, then you can deprotonate this position. Right? What was the other instance in which we switch it up? In this example, where we have two options, what do? Normally, we do this side. But if they specify, they're like LDA, room temperature, you do this side. If they say LDA and -78, then you do this side. If they don't specify, it's kind of confusing, right? So they usually tell you, but if they don't specify, just use your best judgment. But once again, for something like this, where it's very clear that this is super acidic position, you always do that unless they tell you kinetic conditions. No matter how much I keep adding things I think I forgot, I always forget something. Hopefully that's not the case. If I forget something, I'll mention it in the comments. But yeah, that is it. We are officially done with the entirety of OChem. So guys, this is the end. I have one final message I want to say. If you're completely done with hearing my voice, if your exam is the next 2.5 minutes, or if you just only here for the reactions, feel free to dip. This is just a message for those who want to listen. People ask me all the time, why do you do all this? Why do you spend so much time, like 12 hours straight, no food, no water, just pumping out this content? And why do you do all this stuff that you do for the MCAT, like all these lectures, which by the way were so difficult to do? Why do you do all this stuff and you don't get anything out of it? Like, you don't get paid or anything. Some people might say, like, oh, you're doing it for the med school apps. Guys, I already got accepted like ages ago. This has nothing to do with that. The simple answer for me, right? It's true. Like, I don't get anything out of this, but I find this stuff very fun. And everyone knows that if you're doing something that's fun to you, it's very easy to do a lot of it to extents that other people can't fathom. So that's what teaching is for me, teaching and organic chemistry. I'm like pathologically obsessed with organic chemistry. I know a lot of people, when they eat food, they like to watch YouTube videos or just shorts and stuff. For me, I just watch like organic chemistry lectures. It's pretty bad, but that's kind of like to give you an idea of how much I love OChem. I love just spreading the knowledge. So that's like the simple answer. But the more, I guess, deep answer is, if you were to tell me when I was taking this class that there was somebody out there making all these cumulative review videos from top to bottom, going over all the little niche, intricate details, and they're able to let you achieve a perfect score after watching just 1 minute of it, I would have been like, bruh, this is too good to be true. This is unrealistic. Like, you're never going to see that, right? And that is the case. You've never seen this type of a thing before, and you probably will never see it again. But then I also thought, like, what if this thing was actually true? I mean, it's called too good to be true for a reason, because if it was true, it would be a cheat code, which is what it is. I mean, that's what it seems like. Some people, they don't study, they just watch this video and they do amazing. It would be a cheat code. So then I was like, what if I just make it true? I have the ability to make it true, but it does take a lot of effort for sure. But if I were to make it true, can you imagine how much impact there would be on everyone? And so I kind of combined the two things, right? The, I guess, desire to give people things that they'll never ever see again, and my passion for teaching. I put those two together and I developed this whole series of making these videos. And so the reason I'm telling y'all this is because I hope that my actions were enough to inspire somebody out there. As you can see, nobody does something like this, but now you know one person who did something like this. And so if you have the ability to make something that's considered too good to be true, actually true, go and do it. Just be completely selfless and do it with the intention of benefiting other people. Because one day it will come back to benefit you in ways that you probably can't imagine. And this doesn't have to apply to teaching, right? I'm not talking about teaching. I'm talking about like literally anything. If you're good at making music, or if you're good at drawing things or something like that, and you're passionate about that stuff, go do something extra with it and just wow people with it. Okay, that's all I wanted to say. Thank y'all again for watching all these videos. I'm sorry, as always, if this video was super long. Please drop any comments if you have any questions, or if I made some stupid, foolish mistakes. And yeah, I will not be seeing y'all in the next one, because there is no next one. Peace out, everyone.